I think so, yes.
Yeah, okay, thanks. Okay, so what I'm going to do, what I'm going to speak today about is a follow-up of what I talked about last year at the EnKF workshop. But now it's going to be maybe much more complete because I'm going to speak about all the results that we got, but maybe less technical. I'm not going to go into the equations and some of the algorithm. Just more discuss the results and the types of algorithm that we found. And that's it. So my collaborators are there. I mentioned there. So I'm going to focus. So this is at crossroads between data assimilation and machine learning, with the specific goal of trying to learn the dynamics of the dynamics of a dynamical system, or maybe some part of it, not necessarily the full dynamics, and using the combination of data assimilation and machine learning tools. But the specific goal of this talk is to speak about the online way to do so. That is to say, like that sequential data assimilation is usually carried out. As we receive new observation, we usually update the state of the system in data assimilation, maybe some of the parameters that define the system or characterize the errors. But here we'd like also to update the parameterization that we found with machine learning, or even update the full model if possible. So both the state of the system and the model. So that's what I call the online learning. Because usually when you try to learn parameters or a parameterization or a model, then I mean, the natural way to do so is to consider a variational scheme. So trying to throw all the information.
Sorry, Mark?
Yeah.
It seems we're not getting the new slides.
No, I haven't changed. Not yet. Yeah. That's fine.
It's good.
You
Okay.
should be on the outline. Are you?
But we're still on point one.
We're still on point one in the outline.
Really?
Yes.
Is it changing?
Now it's changing, yes.
Okay. Right.
I'll alert you again if it happens again.
Mm-hmm. Let's see. Right. Okay. So first of all, I'd like to explain. So what is the why we combine data assimilation and machine learning?
Are we supposed? Oh yeah.
To see slide 3.
We're on slide 3. Yes.
Okay. Good. Okay. So so a typical machine learning problem. If you want to learn some parameterization or a model or dynamical model, would be to consider this loss function. Okay, when you compare the some observations of the system at time tk, and you you forward it using a statistical model, for example, a neural network, which is parameterized with all the weights and biases of the neural network, and then you compare it to the output, which is the observation of the system at time t+1. Okay, so M essentially depends on P, and we like to learn the set of coefficient P. Okay, but if you want to do so, you need to observe the system fully, because you need to have access to the full state of the system and try to learn through this K. And that's something that clearly we can't do on geophysical system when we only have a partial access to the system and very noisy access to the system. And that's why we, in addition to machine learning or statistical representation of the model, we also want to use data assimilation tools, or the way that data assimilation has to see that kind of problem. So what do? Well, we write, instead of writing the loss function that I showed before, we write this cost function, okay, which can be derived from a pure Bayesian standpoint. We've got the observation departure here. You've got the, so this is the model error term, or the departure from model error. And this actually corresponds to the loss function that we saw before. And this loss function so depends on the parameters of the neural network or whatever way you have to parameterize your model. And as in weak constraint for DVAR, it also depends on the state trajectory within the data assimilation window. So this really resembles a weak constraint for DVAR cost function. Okay, or you can see it as a 4D-var. I mean, there's a matter of there's a discussion about how to call it, but you can also see it as a 4D-var where you want to retrieve the parameters and the state of the system, the trajectory within the window. So the way we came up to solve this, to minimize this cost function and to solve the Bayesian problem is this way, is to first, because P and the trajectory are of different nature, it's actually quite convenient to start with, say, initialize the parameter P, so have some representation, some initial representation of the model, then perform fixing the model, then you perform a data assimilation step, and you carry out this 4D-var, and you end up with an estimate of the trajectory within the data assimilation window. So now you can update the estimate of the trajectory, and you can now fix this trajectory and try to minimize a cost function over the parameters P, so over the neural network. Okay, and so this is the machine learning step. And then you can iterate, so go back to the data assimilation step, then machine learning step, and so on until convergence. This actually should converge because it's a coordinate descent of that aims at minimizing this cost function. So this is it was initially empirical, but we made it rigorous. Okay, now another development in the literature is about the fact that for numerical weather prediction models or for bigger models in the geosciences, this might not be easy to actually initialize this loop and have a first good representation of the model. So one way to carry out this task is actually to start with a physical model. And of course, we've got, at least in numerical weather prediction, we've got pretty good physical model, meteorological models, and so we can use them and add a correction to them, which would be so a statistical correction and neural network correction. Okay, and this is what is usually called hybrid model. And so this can be seen as a model error correction to the physical model, okay, to the imperfections of physical model. And the advantage, of course, is this should accelerate the learning of the full model, and you don't need that much data when you do so. Okay, so this is this was really a variational view on it, and now we'd like to actually go to this online learning. And to do so, there are actually two ways to carry out the task. And the first one is I mean, this is to choose actually what we want to learn as far as the model is concerned, as far as the P coefficients are concerned. So one thing we could learn is actually the tendency of the model, of the dynamical model. So that is essentially the equations of the model. And the other thing that we can learn alternatively would be to learn the resultant of the model. So that is integrating these equations from time tk to time tk plus 1. So, and you can represent both with a neural network. So if you choose to, so depending on the option that you choose, you will have drawbacks or advantages. And for instance, with the tendency, then we've got an entanglement of physical model and neural network, which is good because this is not just adding some corrections, some stochastic noise or any corrections to the model. This is much more subtle than that. But of course, you need the adjoint of the physical model because you have to go, when you compute the adjoint of the full scheme, you need to go through the physical model and the statistical model. Okay, and it's but then it has a lot of advantages because you can integrate it to any lead time, something that you can't actually do the resultant correction. Okay, so both options are interesting and can be considered actually in practice. So in the following, I will illustrate some of the results with the two-scale Lorentz model that I guess many of you know. So it's essentially a Lorentz model, but there is actually two intricate scales, and one is the coarse mode dynamics. So it looks like the Lorentz 96 model, the one scale one, but it's influenced by the fast modes, okay, which are represented here. And okay, which spurs instability in the coarse mode dynamics. So this is and this is quite good actually. This is the model which is interesting to use when you do machine learning, because you'd like, for instance, to represent some of the effects of the fast mode dynamics onto the coarse mode dynamics using a parametrization, so a neural network parametrization of these effects. So that's a good model to play with, to test that kind of ideas. And so what we did here is to use the so this is a full OC. So it's we try to learn the coarse mode of this two-scale Lorentz system. We have observation that we have perturbed, and we want to learn. So we use the one-scale Lorentz 96 model as a physical model. Okay, so this is the first representation, first approximation that we have of the model, and we'd like to correct it to account for the fast scale modes that impacts the coarse modes. And so this is just a simple representation with convolutional neural networks, and they are trained using 4D bar. A 4D bar analysis. Okay, and so if you look at the scores, and this is using, yeah, we actually we test resultant corrections or tendency correction. And when you look at it, that without any correction, that is carrying out data assimilation with a 4D bar, but without considering only considering the physical model without the corrections, that you've got this root mean square error of 0.31. When you implement the resultant correction, then it gets actually better, because you've got 0.28. And when you got the tendency correction, which is more costly, but as a finer description of the equations, then it's 0.24. And when you do when you carry out data assimilation, but using the true model, so cheating and using the true model, then you've got 0.22. So that's a way to evaluate. So this is the way that we had to evaluate those tendency or resultant corrections. Okay. Now let's see about this distinction between offline and online correction. So offline, so far, this was just variational scheme, and we have all the observations and all information that we have, and we try to optimize on the state and the under model, or the parameterization of the model error correction, and you carry out this optimization and you try to find the best solution. Now we really want to update our knowledge on the state, but also on the model as we get new observations. So this is the online scheme. Okay, so to do that, we actually go back to the cost function, which is the one that we're going to use at each step of this online sequential data assimilation scheme. And we make the approximation that we don't have a full background error covariance for the parameters of the neural network and the state. And we've got this pseudo diagonal and block diagonal covariance matrix, prior covariance matrix. And we still got the okay, the usual departure from the observations. Okay, so it's very similar in many ways to the parameters estimation that we can perform in data assimilation. Okay, and this is one of the most interesting results that we have, at least on toy models. Here we use the tendency correction, And so this is time as we get new observations and we use the sequential implementation of 4D-var. We move forward in time, and we compute as time goes by. We compute the root mean square error. And the physical model, the original model, has this error, so 0.31. This is the blue curve, and the and here in red, this is the I think this is data assimilation just using the original model. And then we start. And the green line is the offline correction that we get. Okay. And now we like to see what is the performance of the online correction. So we start with the physical model and we start assimilating those new observations, but that informs onto the not only the state, but also the model. And you see a sharp decrease in the error. And at some point, and this is where it becomes very interesting, at some point it actually gets better than the offline correction. At a point that it's actually going quite close to the to what you would do with data assimilation using the true model. So that's a pretty, I think it's a pretty interesting result, at least on those toy models, that actually potentially on theoretical grounds we can do actually better with this online correction than the offline correction, and we can even reach something which is very close to if we had the true model. Okay, and at the moment, we and actually Alban, Farshi, and Marcin Crust are working hard to actually try to implement some kind of a neural network library onto the IFS system. So the ECMWF forecasting system, forecasting model, and they do so that we can actually implement that type of ideas. And they've got and so they implement that in OOPS, you know, the framework, the software framework that the ECMWF has, and they have started doing that with the QG toy model that is in OOPS. And once it will be achieved with the QG model, it'll be actually not that difficult to implement that on the IFS, because everything will be interfaced properly, and this neural network library would be implemented. So they actually have already pretty good results, and they are very close to being able to implement that in the IFS and test those ideas in the IFS. Okay, now all I spoke about was the this online learning, but it was using variational methods. Okay, in an offline way, when we had a full variational and only one variational scheme, or a sequential 4D-var. Now I want to look at the coming back to something that I showed last year about using local EnKF, so EnKF with localization to learn. So it's really online by nature, and to achieve the same goal. Okay, learning the dynamics. So I won't go into details as I did last year, but the idea again is to this time is to consider parameters again, like global parameters, like parameters of the dynamics, like the one you would have in a neural network, but also local parameters, typically like forcings that you would have in the system. So something that there may be a lot of parameters, but actually you know that they are local, which could help you a lot. And the formalism that we use is the very classical augmented state formalism, where you extend the state to to the state, the global parameters and the local parameters. Okay, so it's really like maybe, as I said last year, it's like an ambitious parameter estimation problem. Okay, driven by machine learning ideas, but it's really a data estimation problem. However, we know that for the parameter estimation literature using the EnKF, there is a lot of holes in the theory. Some of them we have actually filled in last year, and we have done more over the past year and kind of completed our goal. So maybe I'm not going to go into all those details, because I'm not going to go into the equations, but just tell you why this is interesting to do so, to fill all the holes in this parameter estimation theory for the EnKF. So of course we want to consider local ones, local variants of the EnKF, because this is the one that are scalable. So the one you would use on the on the intermediate to high dimensional geophysical model. And we really focused on the difficulty that we have when we want to learn parameters using localization and considering both local and global parameters. And not everything is actually has been carried out in the literature, and there are a specific scheme like the local ensemble square root filter, for instance, which is well suited for global parameters. It could do local parameters as well, but of course it has a cost compared to the EnKF, local ensemble transform Kalman filter, which does very well with the local parameters, which is not meant to deal with global parameters by construction. Okay, so we want to fill in some of the problem. We want to work on some of the problems that we already have for the global parameters and local parameters separately. And also we have finally worked on mixing two types of parameters, because this is typically what we would get in a realistic system, where we've got both forcing to learn and the key dynamical parameters of the system. Okay, and there are the additional subtlety that actually non-local observation, like radiance observations, require covariance localization. Okay, because they are non-local. So that's something you have to consider in addition, on top of what I said. Okay, and so the methods that we have. So I'm not going to show some of the formula or algorithm. Is that compared to what I showed last year, we actually proposed a new implementation of what I proposed last year and improve upon that. For the EnKF, when we want to learn global parameters, okay, and it's actually state rigorously and developed on a well-known scheme, which is the Axoy scheme, so the average scheme, which is empirical, which works very well, but which is empirical. And now we write in a rigorous way how to do it. And okay, and we did also something new with the local ensemble square root filter. And also we have a variant where we can consider both domain localization like EnKF and global localization and covariance localization like local ensemble square root filter. So this is what we call the L square ensemble square root filter. Okay, and what we actually specifically worked and where we propose new algorithm is when we consider both local and global parameters, and we want also, of course, to learn the state. So essentially, we want to learn all the parameters in the model as well as the state. And when you only consider domain localization, so this is what we call the EnKF hybrid machine learning. When we got covariance localization, then this is the local ensemble square root filter, hybrid, because we've got those two types of parameters, machine learning. And when we've got, we have to use, because of the non-local observations, we have to use covariance localization, but also for in simplicity, we want to use domain localization. And we've got non-local observation, which is actually typically what we have in a meteorological model. Then we end up with this L square ensemble square root filter hybrid machine learning algorithm, which should account for variance modeling, variance observation, temperature observations, and whatever. Okay, I'm not going to focus on this because I talked about it last time. I just want to mention that for the global parameters, there is a very interesting theoretical point: is how do we localize the extended, the augmented background covariance matrices, because we have to consider both the state and the global and local parameters. And this is a question that was first, I mean, it was known for a long time, but it has been first seriously discussed by Tiana and Yvonne in this paper, and we continue on that. And so this is one of the latest thing that we got when we got several local and global parameters, or many local and global parameters. So you have to introduce actually a vector of tapering coefficient that have really a very, very nice interpretation, because they are both relaxation coefficient in the EnKF scheme and there are also localization tapering coefficient. So it's kind of a, and there is a condition for the covariance matrix or for the localization matrix to be definite, positive definite. So zeta has to be small enough, and we've got some estimation of how small it should be. So that's an important theoretical point, which is important in practice because otherwise it won't work if you don't respect that condition. Okay, and so this is an example of the schemes that I've talked about on the inhomogeneous one scale Lorentz 96. So where all the forcing F depends on the grid point. And here, this is the so this is the state root mean square error. This is the ensemble size, and this is the curve that you would get from data assimilation when you know the true model. Okay, and this is what you've obtained with the with the EnKF and local ensemble square root filter using the scheme that I've introduced. So we learn the full model. Okay, we only have access to the data. We learn the model, of course, and we learn the we learn the state. So, and the last
just a heads up, 2 minutes to go, please.
So I'm almost done. So the last big example that we played with is the multi-layer Lorentz 96. So this is a 2D model. So there is a 1D. This is the traditional one dimension of the Lorentz 60 one scale Lorentz model, and we stack several of them and couple them to represent the vertical dimension of the atmosphere. And because we want to learn some radiance observations that we have on the system. Okay, and so this is, and we want also to learn some inhomogeneous forcing. So this is typically the toy model that we built to test the full scale algorithm, where we've got the 2 types of localizations, the 2 types of parameters, and the and everything else. Okay. And okay, so I don't necessarily have time to show that, but the point is that actually at the end it works, and it works very well with an ensemble size, which is exactly the one that we expected from theoretical arguments. And it does as well as so an ensemble of 50 members does as well as an ensemble of 140 members without localization. So actually, it's it really supports the fact that our algorithm is correct and working well. So the conclusions here is that so we've built this Bayesian data assimilation standpoint on how to combine machine learning and data assimilations in order to actually learn the model and the state, but using partial and observed observation as we have in geophysical science. We build those online algorithms, so using both variational method like 4D-var and ensemble command filter, local ensemble command filter. And so in the process, we actually fill some of the holes or gaps that we had in the parameter estimation theory with the EnKF. And we have tested that on several toy models, and it works well. And what we're actually currently doing now is maybe more technical, is that we are trying to apply that on the Marshall-Molteni 3-layer QG model, but also on the data of ERF5 and CMIP. And as I said, Alban and Martin are trying to test that on the ECMWF IFS. And that's it. Thank you very much.
Yeah, thanks a lot for a very interesting talk. We won't have time for questions, but you seem to have everything under control, so shouldn't be a problem.
Okay.
And then next up is Nicola. There we go, right? Is that the best mode? Not sure.
Okay, so we have to.
You don't have to sit there.
I'm not sure why. But it seems okay.
Yeah, it's good. Do you hear me well? Okay. Yeah. I'm very happy to have the opportunity to present you my work today. So I'm a PhD student in the Laboratoire des Sciences du Climat et de l'Environnement near Paris, and my PhD supervisor are Philippe Navot and Clément Fablet. And today I will show you my work about learning variational data simulation models with uncertainty quantification. So my work, I don't know why it doesn't work.
So you can't see the top bar, the other participants, although we can see.
Yeah, but I can't change the slide.
Is that what you want?
Yeah, I think it's okay.
And then you want the full screen?
Just
Yeah,
one-
it's all right. Okay, it's not the full screen.
No, it's not about the full screen.
Oh,
It's
what-
just to change the.
You cannot. Okay,
No.
let's try this one.
Ah, yeah, okay.
Yeah.
Sorry.
Yeah, that's okay. Let
Okay.
me. It's already full screen. Sorry.
Okay, so it's a difficult start, but I think now it's okay. So yeah, this work is based on the work of my PhD supervisor, who create an end-to-end learning framework for learn jointly dynamical evolving model like the resolvent Mark just talked about, and also learn the solver in a variational data simulation setting. So we would like to extend this approach to also account for uncertainties and learn not only the pointwise estimator, but a distribution. So just to remind you about variational data simulation, so I remind you the root constraint for the var objective function. So in purpose, I don't mention the term about the background, which is not of interest in our study, but it's mainly made of two terms. One of the observation error and one the model error. So what Ronan did is he just calculate the resolvent to in a neural network framework, and he learned a solver to optimally minimize this variational cost. And both all learned jointly. So now this work enables to estimate the state of the system. But what we want to do is to have an estimate of the posterior distribution of the state given the observation. So to do that, we switch to a probabilistic formulation, in which we use the evidence lower bound equation. So the log of the evidence is the log of the observation, and the lower bound is an expectancy of the log of the probability of a joint distribution of the observation and the state of the system divided by our target distribution Q, and this expectancy has to be considered with respect to Q. So this lower bound here on the right hand side is maximized when the target distribution is equal to the posterior we are searching. So what we're going to do is to parameterize this target distribution by a set of parameter theta, and maximize this lower bound with respect to theta. So how can we do that? So we have to rewrite this evidence lower bound in this formulation. So it is made of two main terms. The first one is also an expectancy of the observation in the state, and the second one is Kullback-Leibler divergence. I remind you the formula of the Kullback-Leibler divergence. So this Kullback-Leibler divergence is between our target distribution and the prior on the estimated state. So if we want to have an explicit formulation of these differences, I just want to say that this is always non-negative. So it has for the following. If we take everything Gaussian, so this is the usual assumption. If we also make an assumption of Gaussianity for the prior of the state, and we search our distribution, our target distribution, in with a Bayesian parameterization, with a Gaussian parameterization. So we can, in this setting, have an explicit formula for the elbow, which is we have. So for the first term, we have this expression, which is something about the trace and the log of the determinant, but this term, which is kind of similar to the observation error, at the difference that we replace our state by the mean of our target distribution. So if we want to maximize this, we have a way to minimize this. Okay, so this is kind of observation term. It looks like the observation term of the 40-ball cost. So for the Kullback-Leibler divergence, we have this expression, which is quite so we have this expression, which is quite complex, but in a general setting, when we don't suppose our prior to be Gaussian, we can just say that it's a function of J sigma, which is not no, but which is always positive. And so if we want to maximize our LO, we have to minimize this J function mu and sigma, even if we don't know it. So that's the point. That's where we use a kind of machine learning trick, a rewriting trick. Instead of considering directly this J, we will consider the function phi, such that J of mu and sigma is equal to the square difference between phi of mu and sigma. So why would we do that? Because it seems strange. We don't know J, we introduce another function phi, we don't know more, but it has an interest. So it's a common reformulation in machine learning techniques for polarization. Also, it's a clear analogy with the model error term of the variational cost. So we could now apply the knowledge of the previous work made on the learn solver for variational data assimilation that my supervisor did. And so it implies in a way a dynamic evolution of mu and sigma. It's a kind of augmented state formulation, even if it's not exactly that, but could remind us of that. So now we have our new variational cost, which is derived from the maximized of the elbow formulation, which is made of this new observational term and a new model error term. I put hat on phi because as we don't know phi, it will be an estimate of phi, and this estimate of phi will be made by a neural network formulation of phi. So we have now two things that are really important in our neural network model. We have phi, which is represented by a neural network, and we have also the solver of this equation, which will not be classic just gradient descent or something else, but a learn solver to optimally optimize in a way the cost of this variational cost. Yeah.
Can I ask a question?
Yeah.
Why do you need to learn the solver?
So because it's an efficient way to minimize this cost. So it's based on some work on learning to learn methods. So yeah, I can show you the references, but yeah, it's kind of really efficient for this kind of problem. So yeah, it looks like that roughly. We have our solver and our Model 5, and they'll communicate in a way in an iteratively based virtual algorithm to minimize the variational cost. Okay, so we have our initial state for mu and sigma, and at the end you have our output mu n and sigma n after the big step of iterative minimization. Yeah.
So you're jointly optimizing the autoencoder and the solver.
Exactly. Yeah, both are optimized or jointly learned. And yes, to have a little more details about that, because here it's really roughly to see that there is two main parts of the algorithm, but we can just have a look at a single step of the optimizer. So on input, we have mu at the k step and sigma at the k step of the solver, and we want to go to the mu k plus 1 and sigma k plus 1 step. So here on the left, mu k is the red curve. I don't know if you can see there from where you are, and sigma is the blue coverage. So we calculate 5 mu sigma, then we can calculate with the observation the variational cost. Then we can make a differentiation of this variational cost, which we put through an LSTM cell. An LSTM cell is a long short-term memory cell, which is quite useful. It's a recurrent neural network cell. It's useful for learning time series and patterns in time series. And then from that, it gives us an update rule for mu and sigma to go to mu k plus 1 and sigma k plus 1. So we have now a model that gives us from observation and initial state outputs, but we have to optimize the whole parameters of our model through a criterion. So that's where we are cheating, because we are considering that in most of the experiments, we consider that we can have access to true states of the system. And so as we're interested in modeling distribution or the best Gaussian approximation of the posterior, the mean square error criterion is not satisfying in this perspective. So we use an entropic criterion that we wish to minimize, and so it's minus a log of the probability of our output parameters, the probability of that we see that the real state is what it is, given that given the parameters that we calculate, which are the output of our system. So we make several experiments to show if it's relevant or not. Because it's a very complex model, but is it working, or is it showing something interesting or not? So we have two synthetic data sets: the autoregressive linear model, which is a real simple model for which we have some benchmark evaluation, and the RN63, and also a real data set, which is the linear discharge measurement network. And we tested in those prediction and reconstruction depend on the cases. So this is for the first one. We don't have to assume that the model noise, for example, is independent of the state. So we tested the two cases. And what is interesting, so for the state independent model noise, we have the Kalman filter is optimal. So we can compare what we found with the Kalman filter. And in our case, we don't know neither matrix A, B, or even C in the case of state dependent model noise. So yeah, we found results of the same order without knowing the model of the error, but we having access to the true values for training. So yeah, that's the thing we have in plus compared to Kalman filter. So as we have results of same order, we can just say that we are doing something that is consistent. So let's go through a more complicated model. So Lorentz 63. We consider two types of Lorentz 63. One is the classic one, and the other one is a stochastic version, which accounts for a natural derivative of the state going to a stochastic differential equation. So that the stochastic version is to introduce some kind of great noise in the evolution of the states. So to visualize it, we can just see how the wing of the Lorentz dynamics look like. So you see that on the right, it gets really noisy when you use this kind of stochastic.
Can I interject once more?
Yeah.
Just didn't understand why not simply add white noise? Why not Brownian motion? What's the deal with shuffle?
Okay, so because it has a physical meaning, which is more linked to real geophysical flows than adding just a white noise. Yeah, and also it's correlated in you see it's rho minus z, for example, the Brownian motion. So it's state related, so it's not dependent in state. So I think it's more interesting for our study. So yeah. So what we can say about that, it's I call my model the model for the Barnett stochastic. So it's a name. It's not a good name, but still it's a name. What we can say is for the entropy. Sorry, I didn't speak about the setting. Yeah, because it's quite important. So it's a reconstruction setting for which we observe only the first variable of the Lorentz on 3 variables at for 8 time steps with 0.01 range of each time steps. And so we've got that for the entropy criterion, and even for emission, we are better that simple and simple Kalman filter for both version. And if we give more observation than simple Kalman filter, it gets better in mean square error, but except for the stochastic one, the entropy is not that good. So I think it's a good way to see that what we are doing is not we're calculating the variance of the data or of the posterior. We are recalculating which is the best Gaussian approximation of the distribution, not only the variance, which is not exactly the same thing if the data or the posterior is not Gaussian. Okay, so yes, to speak about real data, I don't really so we have this data set, which is made of 31 Gaussian stations on the daily peripheral network with 50 years of daily measurements. And so what we did is we just mask half of the station. So we just have 15 stations that will remain, and we observe discharge once every 4 days. So it's a reconstruction task. But here, as we don't have any ground truth for the real state, because it's a real data set, we have to change our training criterion, which was the log probability of the true state given the parameter we calculated. So we just say that we have to optimize with respect to minus log of the probability of the observation we have with the parameters we calculated. So it works because as long as we are calculating a model which is completely data driven and we lack information, so it's only based on the discharge we have, it's really noisy. So the noise on the observation, I think it's not really relevant for. So yeah, that's what I said about the setting. And just to have a visualization of what we did, we can just see this graph. So here yeah, you can't see anything, but yeah, you have to imagine that that there is the probability coverage, which making the 95% confidence interval of the Gaussian calculated, and it looks quite good. Even it doesn't. And so the estimated mean is in red, and the hidden observation are in blue. So because it's a station that is masked during the training, so it's station we have completely to construct. And so what is interesting in this, it's for example, compared to the algorithm by supervised at the 4D VARNet, we don't lose much in MSE reconstruction. But for example, if we use for the model error the mean of the variance for each station on the kind of validation set, we are really improving in the entropy sense, or in the probabilistic sense, with our estimation of variance in this experiment. So yeah, that's what I wanted to say. So to conclude, so we see that based on a 4D VAR-like directional cost infer from the algo formulation, we've been able to give the best Gaussian approximation of x given y. So given that we can train in a way our model with true states, so we don't have to get in prior knowledge on the dynamic, neither on the error. Interesting. And this framework can easily be extended to other parametric distributions. So we have just to say our chief theta. Theta was being a signal of something else. And more complex type of noise can be simulated to evaluate a method for highly non-Gaussian distribution estimation. So yeah, thank you for your attention.
Right, so by my count, we started a little bit late, so we should take 5 minutes for questions if anybody has any. I certainly have.
Maybe I can start with. So if you go back to slide 15, maybe I need some details there. Because if you look at this cost function, so in a way, the first one is a Davis measure, let's say that, and it only depends on mu, right?
Yeah.
It doesn't depend on sigma. And then the second term, in which you have this phi there, it depends on both mu and sigma. So if you want to minimize this cost function, maybe actually you don't have any sensitivity of this y with respect to sigma.
Um, yeah, that's. And you said that I could have minimized, for
Yeah,
example,
I think
the
you can
first.
estimate mu, that's for sure. But I mean, you only have a sigma in the second term, right?
Yeah.
So it means that y is another function. Okay, the simulated y is another function of sigma in a way. So, and then I don't know if you want to minimize this cost function with respect to sigma. In fact, actually, the first term is not included. You only minimize the second term in a way.
Yes, but as long as the second term also complies mu, if I modify mu in the first term. So
Yeah, that's for sure. But I think mu and sigma are kind of independent. So you can, of course, modify sigma and mu. I mean, simultaneously. But if you modify sigma, that will not affect the first term. That's my impression. But I'm not sure if it's detailed in a way. And later on, I think you have this cost function that allow you to estimate maybe both mu and sigma. I forgot the details. Maybe there's something there to compensate for this, but I didn't get the details. So maybe we can discuss that during lunchtime. Yeah, just a comment.
Any more questions? Yeah.
Question. So, at some way, because you have to think about online.
I see.
So at the summary page, you mentioned that your like results are the best. I was wondering like, what's the best in which metric in terms of?
in which?
So I think at the summary stage, you mentioned in Gaussian case, you obtain the best solution. I was just wondering like the best is in terms of which metric?
Yeah, in terms of entropy. So to measure the distance from the distribution, the posterior distribution, and the Gaussian we estimate is the entropy. So it's our criterion.
So you're saying that when you use the elbow loss, it gives you a solution that is best in terms of entropy.
So it's two different things: the elbow loss and the entropy. So the elbow loss is what is minimized in the solver, but what is the output of the solver? To look how good it is, we use the entropy.
Yeah.
Okay.
So theoretically, when you use the elbow loss, you obtain the best approximation in terms of entropy.
No. You mean if we yeah. That's I think you're thinking about that. Yeah. I mean the maximum of the elbow is the posterior distribution. So if the elbows was 0, no, not 0, but equal to log the evidence, the problem is solved. But there are many things that are taken into account. We don't minimize exactly the elbows because we don't have phi, so we have only an estimator of phi. Also, we can't evaluate exactly if the distribution are equal, so we have to find a way. That's where entropy is coming in. But in fact, if the elbows were able to do a lot of the evidence, it would be perfect.
Okay,
I think maybe we should break for lunch.
on the last.
那个麦克风呢？
哎，这个怎么不太 work 啊？你插进去。
我给你弄那个麦克风吧，声音大一点。
我看一下这个。
这个那个开光。这个就是
怎么弄的？
就这么
耳朵上面是吧？
对，就这样。然后这个就是现在是光的。
OK。
我看一下摄像头，觉得应该可以。
Sorry, I know you're just about to start. Sometimes.
Yes, closer.
Yeah. Projection.
No, on the.
Yeah.
It's better.
The screen. Yeah, right. Yeah.
Okay, I think we are ready to start. Is everyone back? No? We start anyway, so welcome to the next session. So the next speaker is Henk Schall from Virginia Tech, so please.
Thank you very much. Yeah, I understand that this is a. Thank you for coming to my talk. I understand you have to cut your lunch break by half an hour to attend my talk, so I will make it a little bit informative, I suppose. So, as I wrote here, I specifically write my department. I'm from aerospace and ocean engineering, so slightly different from the typical application background of other EnKF users and developers. I myself actually educated as a civil engineer, and so well, it's engineering. So our talk is about using ensemble common method. Well, we call it EnKF, but I don't really do filtering. We have a steady state problem, so it's ensemble common method for learning temperature models from indirect observation data. So I think there's not a need of. So before I dive into the domain specific things. I want to talk at a high level. What are we doing? We are not estimating state. Yeah. So we do not have this problem of not knowing the initial condition and boundary condition and those. Mostly, our uncertainty, our problem coming from a model, a closure model that we don't know. Right? The most typical ones would be not for me, but for civil engineers, the stress strain relation, right, of a rock, or for if you are simulating a human body, the bones or the mass, the vessels. These are the constitutive relation. Right? So I gave a few examples here: stress strain relation, relative permeability curve, right, to get a Kr from S from the saturation. So these we call constitutive relation or closure model, and sometimes it's called parameterization in atmospheric because it's usually just a few parameters and to describe the model. But closure model can be quite significant in turbulence modeling. We do not have algebraic relation. We have a PDE. Sometimes a lot of PDEs. The number of PDEs in the closure model is more than the momentum and equation, momentum and mass equation itself, right? So I will stay as a closure model or model. What do we mean by indirect data? It's again, we have to invent some terminology as the field evolves. Yeah. So usually, if you have the, let's say, stress and strain, right? You want to learn a model, you can do this offline or independent of the solver. You don't need to have a FDM, right? Simulator. But in this case, you can do it with like theta neural network, theta line, or theta whatever model that you choose. But typically we do not have this data. It's difficult. Sometimes it's not. It's a hidden state that there's no access. Right? It's a state that does not have a physical meaning. In our case, now we have a so-called renal stress. Right? The Y. In our case, it's a renal stress. It's very difficult to measure, much more difficult than a velocity. So we call it some kind of a hidden state. So, but if we have that data, that Y, we will plug it into a physical solver, FEM, CFD solver, whatever, and then you get your velocity field or your drag and pressure, something like this, right? Those is what you can measure. Yeah. So we have two different things. One is the closure model, and the other is the physical solver. They are of course coupled, but I single them out. So with the displacement and velocity, you can push the process to get the, let's say, deformation or leave the drag or oil production, and these are the quantities that you can very easily measure. So that's the context of this of our work. So since the former presentations, a lot of speakers talk about machine learning and data simulation, it's very clear that they share a lot of similarity and some differences too, right? Particularly between variational data simulation and machine learning are really indeed very, very similar. So I'll just skip this. So let me start with the context, domain specific. We are interested in turbulent flows, right? I think most of you had used the two modes of transportation to come here, right? Aircraft and the boat, right? And all of these, the fluid dynamics is very important to calculate the load and stability of these vehicles. Nowadays, the industrial CFD, computational fluid dynamics, relies almost exclusively on Reynolds averaged Navier-Stokes, which is a kind of a low fidelity model. We call it RANS. It will be referred to frequently in this talk. And there are other methods such as LES, large simulation and direct simulation are still too expensive, particularly if you're talking about design. In design, you have to make thousands of simulations, right, to optimize and to analyze. So for those, you have to rely on the low fidelity RANS model. So just a little primer review. You don't have to understand those, but it will help to see what we are doing in so-called RANS simulation. You have Navier-Stokes equations, you can solve them, but if you resolve all the scales, it will be extremely expensive, particularly for high Reynolds number flows. If Reynolds number is defined somewhat, you can think of it as the ratio between the largest scales and the smallest scales. For high Reynolds number, that ratio is very large and it's very expensive to resolve. So in RANS, what you do is you decompose it into mean and fluctuation. So by construction, this is already kind of a steady state, right? Because all the fluctuations are singled out. And then you plug in this into the original Navier-Stokes equation, you get a so-called RANS equation, which is very similar to the original, because all these, by definition, the mean of the fluctuation is 0. So for all the linear terms, you just replace the original velocity with the mean velocity, except for the nonlinear term. Oh, wait. For the nonlinear term, that is the convection. And for that, you have a covariance term between the different component of the velocities, and which we call tau. And because it behaves very much like the stress, we call it Reynolds stress. It's not linear stress, but it behaves like that. Very interesting thing is to note that you have an exact equation for this unclosed term. Okay? But to solve it, you have to close these other unclosed terms. Right? So this could be one of the ways to close the Rein's equation. Okay? Yes.
Is there a small u or capital U in the last equation? Or should it be
Oh, if you get capital, good point. Yeah, it should be capital. Yeah, yeah. So since 8 years ago, I did do some data simulation. So it will be. We know that we have a problem. We have uncertainties in the Reynolds stress field, right, which is provided by closure model, and we say, okay, let's perturb it because the Reynolds stress provided by the deterministic model is not accurate. So we inject some uncertainties, but you have to do it in a very disciplined way because it's a very high dimensional field. If you have 1 million cells, which is a small simulation, right? Each cell you have 6 degrees of freedom because the Reynolds stress tensor is a symmetric second rank tensor, right? So 600 degrees of freedom is a lot. So what you do is you do some dimension reduction. You represent it with some mode decomposition, which I'll explain. But in any case, you perturb the Reynolds stress, and then for each of the Reynolds stress perturbation, you plug it into a Rein's solver, right, which we call propagation. You get the velocity, and then you proof the process to get the lift and drag, and these things you can measure. And then you do the typical EnKF, and you do the analysis to compare the observation data and the prior, and then you do the update. You change the Reynolds stress perturbations, and you do this again. So this is assuming that you have measurements, right? Measurement data of velocities. Yeah. So there are some kind of dimension-based things we have to take care to make the Reynolds perturbation realizable. Meaning it has to be a covariance of some random variable, right? It has to be basically positive definite, positive, at least positive semi-definite. And by mapping into a barycentric triangle, which is done very frequently in the modern community, we can order that constraint at each single point to have a realizable Reynolds stress. And we also need to make it smooth because these fields are typically quite smooth. And what we do is we assume Gaussian random field, and then we use the Coulomb-Love expansion to expand the Reynolds stress, and basically these are the modes. And then by doing so, you reduce the dimension of a very high dimensional Reynolds stress field to maybe a few dozen modes. So you end up with a parameter estimation. So these are the domain specific. I don't think there's anything for you to carry away, but I'll go through it anyway. So this is the test. We have a flow over a periodic hill. The flow goes from left to right, and if you have data at these locations, what can you do to improve that? And you can see this is the prior. The black is the truth, and the red is the baseline. It's basically the K omega K epsilon model. And you can see it's quite far away from the truth in the recirculation zone. And in the perturbation with the perturbed Reynolds stress, you can see it's everywhere. So there's indeed quite a lot of uncertainties, and this Reynolds stress uncertainty affects the velocities. Okay? These are the velocity profiles. And when you incorporate the velocity measurement, you will get to the posterior, which is a dramatic improvement, particularly in these regions that with the recirculation. So that's our way of doing data simulation. Yes, Patrick.
Just a brief clarification. The Reynolds stress covariance or tensor, it's a field?
It's a field, yeah. Yes. Every point, yeah. Yes. And it's modeled and it has uncertainty, and we have to figure out this uncertainty by using data, reduce this uncertainty using the data.
Oh, yeah, I see it has excess in our.
Yeah. So there's another case which is a square dot. So the flow goes along the pipe, and because of the imbalance of the Reynolds stress components, you'll have secondary flows in the plane. This is what typically what we have in a river, and these flows will result in excessive riverbank erosions. And typical models referred to as a linear additive velocity models used the most frequently in engineering. They can't capture the secondary flows because they're isotropic. And by incorporating data, again, so this is the cross-section of one of the planes, and by incorporating data, the black is the truth, and the red is the baseline, and the cross means data. By incorporating data, you can improve the predictions across the board, even in the regions that we have no observation data. Yeah. So this is the data assimilation work we did like eight years ago. Now we have a problem though. It's all very nice, and it kind of at the time is also very novel. But then my department head said, well, it doesn't make any sense because your design aircraft, you don't have data, right? For design, it doesn't hold. So what we want to do is to have something that can support design analysis and optimization. So if I give you data on this configuration, you should be able to predict on other configurations, right? You have to be able to generalize, not in one system. So that's the key question that we want to answer. Now, let's look at this situation where you have data, right, in these situations, but can you learn something that is useful for a wide range of flows, or at least in similar flows that are different? Yeah. So in the literature, people have done this all the time. For example, you can use parameter tuning, right? In the Tempest model, you have a lot of parameters, and you can tune it to one flow and then predict the other. Right? And you can do it more rigorously by using adjoint. This has been done for decades in aerospace, in aerodynamics. And you can also do data assimilation, as I did. Right? You minimize the discrepancy with the observation by tuning the Rhesus shear field, but it doesn't generalize. Yeah. Now you could also say, let's just represent the Tempest model with a neural network. Okay, and then you tune the network weight by minimizing the discrepancy with your observation. That y could be your velocity or your drag, but it's typically not the Reynolds stress itself. Yeah. So that's the idea. So we actually started with adjoint. Yeah. So we represent the Tempest model with a neural network parameterized by weight vector W. You plug this into the solver. This is the typical CFD solver. And then this will feed into the tau. And then you'll get your velocity. And then with the observation operator, like post-processing, you'll get quantities like a drag, lift, and this integral quantity. And then with the adjoint, you will get the gradient of the discrepancy with respect to the weight, okay, dj dw, using chain rule. Yeah, the first part is the discrepancy with respect to tau. You have to get it from adjoint. You can write the adjoint, the PDE for the adjoint velocity, and the second part you can just do an auto differentiation of the neural network. Okay, so it's all very nice. But the problem is that it doesn't work very well. The adjoint equation is very stiff. It's very difficult to solve. Or maybe it's just I didn't do it correctly. I don't know. I never knew because it took us so much time and we didn't get anywhere. Well, we published something, but it didn't work very well. So then it occurred to me, maybe just use EnKF, do the same thing. You have instead of inferring the real stress, you infer a model, okay? A Tempest model that parameterized by W, okay? It will, for every point you have a velocity, I will map it to Reynolds stresses, right? So it's point-wise. Now everything else is the same compared to the data assimilation, except that you are updating the weight W, okay, from the velocities or some sparse measurements. And so I just want to point out that this is a little tricky to present this this model, but think of this Tempest model as just a G function that maps the invariant of the stream rate, okay, to the coefficient of the mode to reconstruct the Reynolds stress. Okay, so now from now on, just think of the G function is a Tempest model. Theta is the invariant of the stream rate. Okay, because you can't really use tensor, you should use the invariant. Okay, now we use a true model, a synthetic model, yeah, that somebody else has a more advanced model. We treat that as true synthetic model, yeah, and that's what Femcon was speaking. This is identical twin because you should be able to recover that exactly because it's identical, right? If you use DNS data, maybe your model cannot do it at all. So this is in her terminology is identical twin. So you can see we did quite well. Not very good at the low stream rate situation, and particularly here another component of the model. But that we can explain because in this model, if you plot the marginal PDF, most of the mass fall into the high stream rate, high theta. So if you don't have that data in your case, you're not going to learn that part of the model. So we're fine with it, yeah. And we know how to fix it. If you just bring in some more cases, more diverse cases, you can fix it. So we're okay. So we compare the baseline, which is just a constant. There's no variation in just a coefficient. Now with adjoint ensemble, we more or less get the same, even though they are run in different ways, but they are qualitatively similar. Okay. And there are some other quantities. This is the different component of the Reynolds stress. You can see on the top is the ground truth and the adjoint base and the ensemble. Basically, they are more or less similar. But of course, in terms of cost, the ensemble method is much better, right? Because first it converges very fast, 50 time steps, at most 100. And for the adjoint, this is the conservative estimate. Usually it takes much more to converge. And I think we suspect that this is because it's the first order optimization. It doesn't have the Hessian information, while the EnKF implicitly account for that. And of course, ensemble method is parallel, right? You can run different simulations on different cores. So for us, 6 hours, done. Get the similar results. And at least for our particular implementation, I cannot speak for others. So I'm not an expert in that. But for our experience, ensemble method are much more competitive.
Before you leave,
yeah.
I just want to make sure I understand. So the neural network plus the adjoint, that referred to the chain rule.
Yes, exactly. Yeah.
And then the ensemble method, and the ensemble method, you're not using either of those anymore. You're just using an ensemble method to compute the entire.
Yeah, we have a new level, but we're not using the gradient for now, at least.
Yeah.
Okay. So it's a little weird. I will address. But the good thing is that you can generalize. You train on you can see this on the blue profile. You train on this flow. Now you can extrapolate to a slightly different flows, have a different slope. You can stretch it, right? So because it's kind of similar, but it's not the same. And without going too much detail, it's basically I can point out that the error rate is is kind of significantly smaller than the baseline. So if you don't do the training, just use the K epsilon model that is used in industrial. This is, of course, we use this to pre-train. How do you get the initial ensemble? We pre-train it, okay? So that part is a little detailed, but in the end, the conclusion is that it can improve and it can generalize. Right? So that's all very nice. And we also did another test that what if we don't have that many velocity measurements? We just have like one number, that's the lift. So think of it as your oil production, you just have the production rate, right? Without any detailed measurement in the field. And you can still do that. You can say, in this case, we train on two different flows, angle of attack of 8 degrees and 14 degrees. 8 degrees is like a kind of a nice cruise conditions, or maybe it's a little bit higher if the flow is attached. For 14 degrees is separated. Okay, typically the K epsilon model would have difficulty getting this separated flow because it's not developed for this kind of flows. And you can see from experiment, okay, here this is the lift coefficient, the K omega model. Okay,
method can overpredict that. Yeah. But when we tune the model, we are able to match the lift coefficient, and the pressure distribution along the airfoil will also match. Okay? And if you have no airfoil, you're familiar with this, but it doesn't matter. That's basically we're tuning the model. But does it generalize? What if you are doing the simulation at a different angle of attack? And we can see that it generalized quite well. So these two green lines, 8 and 14, is our training. And we tested on a wide range of angle of attack. So the red is the baseline. It overpredict the lift coefficient in the separated flow regime. And with the learned model, even though at all these locations we do not have data, right? We only have data in the green, two green lines. Yeah, two angle of attack. This is the angle of attack versus lift coefficient. So it does generalize. Okay, how does it achieve that? Well, we kind of see that this is the velocity, the pressure and the velocity, and you can see in the 18-degree scenario, the separation bubble is much larger in the learned model. So it will separate earlier. When you have separation, your lift will decrease. So it's kind of the model kind of tuned it such that it predict a much larger bubble that that matches the lift coefficient, and which is physical. Physics indeed, the baseline model delayed the separation point too much to miss that kind of feature. So I only have a few minutes, so I comment on what we have been doing. It's a little crazy because you use neural network, right? But you didn't use the best part of a neural network. That is, they're very cheap or almost free analytical gradient, right? So, but I can argue that in many cases, well, the first justification is that it works, yeah. And neural network is very expressive. You can have a model that could be valid for a wide range of flows. Right? That's very important for autonomous modeling. And second is sometimes you would have direct data and indirect data. You have velocities, lift, but you could also have rate of stress at a few locations. Okay, so you can, for this case, you can augment the cost function to include the discrepancies in the direct data. And with that, you will revise your scheme to include that part and this part. This is what we did 2 years ago and I presented last year. That is, you add a term that involves the derivative of that neural network, the D prime. So at least in this case, it's kind of justified. And you can see now if we only have very few data points, 3 points, but at this 3 points, we have both rate of stress and velocity. That's both direct data and indirect data. And you can have a dramatic improvement compared to the case where you only have indirect data, because you are learning a hidden model, right? You are learning a closure model that gives you some hidden states. If you do not constrain it, you could learn something very wrong, but it gives you correct measurement, correct integral quantity anyway. As long as you constrain the hidden state a little bit, it helps dramatically, because you already have a constraint that your prediction Y has to give you the correct observed quantity, right? So I think this is a very important point that you have to constrain what you learn. Right? So again, it's this just shows that having direct data is better than direct and indirect data is better than having indirect data alone. So I think these are a little in detail, so I will not go into too much, but I will just leave it here. And if you are interested in this, we have a archive online. So I will just leave it here and take questions using the next few minutes. Thank you very much.
Thank you for a very nice talk. Very nice, because I understood like 50%, and normally I only understand 10%. But it means there's still significant gaps. So I didn't quite catch, for example, is it really the difference between your data simulation approach from 8 years ago and your more unified approach?
Yeah, okay. Yeah, so basically it depends on what you infer. In the data simulation, I infer what is my renal stress? What is the best renal stress that gives me velocity that matches my observation? Is that clear? Now, yes. In this approach, I ask a different question. Not that what is the renal stress, but what is the renal stress model or terms model that can map every velocity or velocity gradient to a renal stress that gives me agreement with that. The second formulation can extrapolate, right? Can generalize, because if this model gives you good results in this case, maybe a slightly different case would work. But as opposed to the data simulation, it's very hard to generalize because you are given a field, right?
That's also what I suspected. So very glad to hear that. Also, I appreciate the brutal honesty about it didn't work, and you published that it didn't work.
Well, I think it's nice. It's a nice try, right? It didn't work very well. It takes long to train. It doesn't mean that it has no value. I think we published it. We stood firmly behind it, and we published the code and everything so that people can look at it. I think it's a nice idea. It's still novel, but it's very expensive to run, and we're not able to converge in many cases. And in our latest paper, I did a very honest comparison, like these two cases, there's two methods, which worked and which didn't work, and that's what we learned. Okay, but maybe somebody else who are smarter on adjoint could make it work. I don't know. I'm not an expert in adjoint. Is extremely difficult. I reached out to many people, said, can we collaborate? I said, oh, I don't want to do adjoint anymore. I'm moving to it. Yes, I don't know. I mean, we have Virginia Tech, we have quite some expert agents I do, and I also talk to other people from TU Delft who are formerly expert in adjoint, but they don't want to work on adjoint with me. So I'm back to ensemble again. I don't know if it's a sentiment, like nobody speaking about it, but my impression is that it's so difficult to maintain a complex code, like CFD code, like OpenFOAM. That's what I use. It's very widely used. It still doesn't have a nice adjoint. I think somebody in Aachen, they tried to build one, but it didn't work very well. It's so expensive. Like do a channel adjoint takes like a 35 gigabyte of memory. It's insane.
Thanks, Heng. Your last remark triggered when you mentioned TU Delft. I feel I need to respond. I do think in some areas there is an increased interest in adjoint models, also because you see kind of linearization techniques happening also in forward models, and they work quite well with machine learning.
Yeah, exactly, for that reason.
So I'm still planning a project with Dennis Voskov, one of my colleagues, who is building its object-based linearization. So it's a way to also construct adjoints. So you need to find the right models that do have an adjoint, and then I think variational methods and adjoints can be very powerful. And exactly what you show here, the link with machine learning is a very interesting one to explore further.
Thank you for noting that. I think I definitely should learn more about adjoint. It's quite difficult to understand this. Thank you.
Yeah, then I think we should. Okay. Yeah.
One more. So I'm wondering, how is it sensitive with respect to which regime you are? Because you showed this. I mean, you showed briefly this triangle for the Reynolds stress.
Yeah.
Like there are these three angles, right?
Yeah.
These specific regimes. In each angles.
Yeah.
So this methodology, you can choose the Reynolds stress in any part of this triangle, or is it more difficult to do it for some Reynolds stresses than others?
Yeah, this is a question we have not investigated, and this is the think Walter Anthony and his collaborator in Stanford, they did a lot of this manual perturbations. And we here, I use it in my earlier work to guide my perturbation of Reynolds stresses so that I don't go too far out into the unrealizable regime. But the sensitivity thing, I don't have a good answer to your question. But I think it's a very interesting point.
Lourdes, você me manda o IBAN do cara, por favor?
Thank you again.
Thank
I
you.
think we need to move to the next.
Yeah.
Sim.
Next is
I think you need to mute all the. Yeah, I will mute.
then we start speaking like a class like this. If you want to use this format, so this is
Hello. Testing.
Yeah, I need to.
Hear me? It works.
I need to share. Yes, I need to share for you. Yeah, try again. Can you turn it on?
Test. It's turned on, right? Hello? Is it working? 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 I guess so. I guess it's working.
Patrick, can you hear?
Hey,
I hear.
you hear me?
Yeah, but maybe it's just your natural voice. I'm not sure.
Okay, I'm gonna speak up.
Okay.
Okay.
I think it's fine. So the next speaker is Sung Kim from Kigam in Korea.
Okay. Hello, I'm Sung Kim from Kigam, Korea Institute of Geoscience and Mineral Resources in South Korea. And personally, I'm really happy to be here in person on site in 4 years since the last EnKF workshop in 2018, as far as I remember. So I'd like to thank my co-researchers, Kyung-Wook, Jung-taek, Hun-young, and Baeyeon. Okay, without further ado, in my presentation, I'd like to talk about recurrent application of pseudo-ensemble smoother for calibration of generalized reservoirs using convolutional autoencoder. It doesn't work. Okay. Okay. Thank you.
I think now the remote control should work.
Okay, I'll divide my presentation into the following 5 parts. So let me introduce you history matching very briefly and ensemble-based method such as ensemble smoother and ensemble smoother with multiple data simulation. And here the proposed method is ensemble smoother convolutional autoencoder, so-called pseudo ES as well. And let me show you history matching results in 2 cases by the proposed method, and then let me wrap it up with conclusions. So, as you already know, in petroleum engineering, ensemble-based methods are applied to history matching, and the updated parameters are geological parameters such as permeabilities and porosities and rock faces indexes and something like that. And those parameters are updated or calibrated according to the discrepancy between history and model responses of reservoir realizations. In spite of many advantages of ensemble-based method, we are bound to face some problems such as geological plausibility and computational costs. So we should be interested in how to maintain geological plausibility and how to decrease computational cost all the time, right? So among ensemble-based method, there are ES and ESMDA, and they have the pros and cons.
as you already know. Over here in this slide, let's say we have the true field and the initial ensemble composed of 100 realizations. Then if it is ES, then it's going to take 200 reservoir realization simulation cost. On the other hand, if it is like ESNDA, it's going to update reservoir realizations with some multiple assimilations, literally. So let's say it is 4 assimilation sessions, then it's gonna take 500 realization, reservoir realization simulation cost, right? So, so generally and typically, ESNDA brings a better performance history matching wise compared to ES, but it takes additional history, reservoir simulation cost 300 times over here. So I got motivated with that issue, and I wondered how to raise history matching performance and lower simulation costs at the same time. That was my main research motivation. So before getting into my proposed method, the default of ES and ESNDA was designed as the following figure. So in figure A, first, channelized reservoir realizations were generated by geostatistical method, SNESI, and the initial ensemble is composed of randomly selected reservoir realizations from the entire pool, which has 1,000 reservoir realizations. And it goes to figure B, and reservoir simulation is conducted for the initial ensemble. And then those geological parameters, in this study, it is like rock facies index. Those parameters are transformed by K singular value decomposition to extract main channelized reservoir information. And then it goes to figure C, and those parameters are updated according to Kalman gain. And then it goes through post process to assign binary rock faces, sand or shale in this study. And then if it is ES, it goes to figure F, and then it is done with a final prediction for final ensemble. But if it is ESNDA, it goes back to figure B, and it is repeated until it gets to the target number of assimilation in ESNDA. So practically, this is the key slide, and this is actually all you have to understand. So the proposed method is called ensemble smoother convolutional autoencoder. I named it, and it is also called pseudo ES. Okay, first in figure B, conventional ES is applied to history matching, and then we acquire the updated ensemble. Okay, then these initial and updated ensembles are going to be input and output of convolutional autoencoder as shown in figure A. So this convolutional autoencoder is trained with those data. And then after training in figure C, we expect that the trained CAE had learned a certain way of update of ensemble smoother, even though we don't know what is going on, what it is exactly. So we put some ensemble into the trained CAE, which is practically one assimilation. So we expect the trained CAE is able to give us the kind of updated reservoir image as shown in figure D. So it doesn't take any other computational cost anymore. Anyway, that procedure is repeated until we get to a step criterion, which is 3% basis variation before and after assimilation in this study. And then in final ensemble in figure F, reservoir simulation is conducted to predict final reservoir behaviors. in ESNDA, as you already know, it takes reservoir simulation cost in each simulation. On the contrary, in the proposed method, it takes only 2 simulation sessions for the initial and final ensembles. So if ESNDA over here, let's say it takes 4 simulation sessions, then we would be able to save 3 simulation sessions by the proposed method. So, okay, I didn't give you some detail for convolutional autoencoder. So these slides gives the details of construction of convolutional autoencoder. So actually, it doesn't matter how it looks like, how it was designed. All you have to know is that it was properly designed to extract some channelized reservoirs information, essential information, and reconstruct it into the original reservoir dimension properly. So that's all you have to know. So in this study, I applied the proposed method to 2 cases, and both of cases are gas reservoirs with an aquifer. So let me show you the first case first. Figure A is the mean of initial ensemble. Over here, so this is the average of 100 ensemble members. So this basis index, and the yellow part means that a sand channel part, and blue part is shale background. So you can see that. And this is the reference field of case 1. And there are 16 wells. So half of it on the channel, sand channel, the other half of it on the shale background. So figures B to E are the results of the proposed method, and figures G to J are results of ESNDA. So according to figure E and J, as you can see, they brought like quite good calibrated results. So they are quite similar to compared to the first reference field, even though there are some improperly connected part and the improperly broken part. Other than that, they are generally good matching results. So this is the cumulative water production results. So as you can see, there are mean and standard deviation of RMSE in each figure, all of it or over it. And the first row is the result of the proposed method. The lower ones are from ESNDA. So as you can see from the proposed method, it is bringing generally decreasing trend of mean and standard deviation of RMSE, which is a good thing that we wanted to do. But on the other hand, in ESNDA, it shows like overall okay level, but yeah, it shows a little bit increasing mean and standard deviation, but it still stays what can I say, nearby the reference field behavior. So both of them were okay level. And this is the result of well gas production rate. For your convenience, or for my convenience also, I presented well number 4, 7, 12, and 15 out of 16 wells. You know, it's due to the paper, the space. So the upper ones are the results of the proposed method. The lower ones are ESNDA. You can see figure A and E, there are big discrepancy, large discrepancy between the reference behavior and the updated ensemble yet. But the over oscillations over here in figure D and H, both of the proposed method and ESNDA, they brought well-matched results, the way I see it. So even though there is some still a little bit of discrepancy, but generally was okay. And this is the well water corruption rate. So it's the same format with the previous slide. So likewise, there are quite large discrepancy between red lines, and blue lines. But the overall simulations, they are getting closer and closer over simulations more and more gradually. So both of them were okay. I wanted to show you results quantitatively. So I'm showing you RMSE results in histogram format of for WGPR, WWPR, and well bottom pressure from the left to right. So the first row is RMSE result of initial ensemble. So it is supposed to be quite large, but as you can see, the red arrows. So generally they are going to left side, which means their RMSE is decreasing, and also their variation is properly decreasing. So we are happy about it.
Sorry, I can't quite see here from afar the legend. Could you just clarify the panels a little bit more? Where is ESMDA?
Yeah, sorry for visualization. These are ESCAE, the proposed result, and these are ESMDA results. The proposed ESMDA, the proposed, the ESMDA. So yeah, in both generally, the sum up is like going to left. Okay, from now on, this is the result of case 2. The mean of ensemble is still totally same. Yeah, it should be. And the figure F is the reference field of case 2. So there are main three channel flows, kinda. And the upper ones are from the proposed method. The lower ones are from ESMDA. Likewise, a quite similar channel pattern in figure E and J, but they are improperly connected and improperly broken apart. So that's a shame, but generally it was okay. Let's see the history matched results.
One more question.
Sure.
Is this another realization of the same problem, or did you change the parameters?
Oh, okay. Initial ensemble is totally same, but I just changed the reference field because I wanted to see. So okay, this is the cumulative water production result. So it's a totally same format with the first case. So both of them are going to closer the red line, reference behaviors line. So we are happy about it. And this is the well gas production rate. So yeah, they are showing a little bit different behaviors compared to case 1. Yeah, understandably. So there are still big discrepancy, and overall simulations is going to the red lines over and over. So yeah, there are some difference of performance over here and over here. So in some cases, yeah, the proposed method was better. In other cases, ESMD was better. So it's like, but both of them were okay the way I see it. And the well water production rate. So you can see the overall matching performance. Okay, yeah, this is also same format with the previous slide. So RMSE is like red arrows, they are connecting the mean of RMSE. So yeah, you can see the big picture. So you can check it out, like how they go to the left side. So okay, finally, I wanted to compare ESCAE, the proposed method, and ESMDA in both of cases in WGPR, WWPR, WBHP. So in case 1, generally ESCAE was better, showed better performance than ESMBA. So you can see, you can compare this value and this value, that one, this one, this one. But on the other hand, in case 2, ESMBA was way better than ESCAE. So over here, it's hard for us to tell which method was like way better or way worse than the other. So it is hard to say, I know. But my point is over here, both of them were okay, decent results. So, okay, let me wrap it up with those following 4 conclusions. So first, ESCAE, the proposed method, showed it's was validated to boost ES or even ESMBA according to comparable history matching performance, saving for simulation costs. And the way I see it, that was affordable, that was available thanks to GPU computing power, which took only 15 seconds for convolutional auto learning. So the way I see it, it is a really affordable computing time. And third, ESCAE gave better history matching performance than the first update of ESMBA. It's not that like ESCAE can alternate ESMBA or something like that. It's not like that. But under a specific circumstance, ESCAE could like give better performance than ESMBA under some condition. And finally, we can say we expect that ESCAE can be some complementary method for ESMBA with affordable computational cost, cheap cost actually. Okay, thank you very much for attention. I would be happy to take any answers. Okay, thank you.
Thanks again for a very nice talk. Again, I could understand almost 50–60%, so very happy there. I also appreciate the fact that you had repeat experiments. Not everybody does, so that's very nice. You know, just changing their realization. I surely missed it. Are you running the same number of iterations or more iterations? Let's see. This is cheaper, I guess. If you run more.
You mean same number of assimilation?
Update steps.
Oh, okay. Over here, okay, I'm gonna have to show you this one. Over here, as this is stop criterion in the proposed method. So when basis variation before and after is less than 3%, and we are going to stop. And what can I say?
This is so cheap, you can run many, right?
Yeah, so it happens to be 4 times like ESMBA. In ESMBA, in the first place, we set up 4 assimilation times, and over here, although I set like as 3%, but by accident, it ends up like 4 times assimilation. Like this, let's say it is 3rd time, I guess. So it's like first time by ES, and the ESCAE first application, second application, and 3rd application. So practically, in terms of just the number of assimilations, then they are same, 4 time assimilation sessions. So yeah.
And so I also think it's a very original idea. You know, since you're using some kind of machine learning, I'm not familiar with CAE. It's kind of like building a surrogate model, except when the normal application of surrogate models is from learning to go from parameters to observations. And here if I'm correct, you're going from observations to common gain rates. Is that correct?
Sorry, could you reiterate?
Yeah, just trying to compare to the usual use of surrogate models, which I guess we can pass machine learning to CAE
Mhm.
as, you're going from residuals or observations to common gain.
Okay. I'm gonna have to it's better to see over here. So yeah, so for the first time, in figure B, ES is applied just once. Then we are going to acquire, we have initial and updated ensembles, and they are going to be input and output for this neural network. So I expected, I don't know what is going on in this convolutional autoencoder in neural network, but I expected it to be learned some certain way of update between initial and update of ensemble smoother. So yeah, I expected it would be able to learn properly. So it's going to function like pseudo ES. That's the reason why I called it pseudo ES. So okay, thank you.
I think my question is the same as your last, maybe. So I was also interested in this training of the autoencoder.
Training.
Yeah, the training of it. So
Okay.
well, what you said now maybe answers it, but so you start with you have an initial ensemble, or you have a set of initial ensembles, and then you run the forward model, you run the dynamical model, you run the ES update, and you use that as the response. Is that correct? Then you train the autoencoder with the initial ensemble as input, mapping to the output of the ensemble smoother. Is that how you? So what's your training database?
Oh, okay. let me get it clear. So this is an autoencoder. So in conventional autoencoder, it is supposed to have the same input and output data. So it should be the same each other in conventional autoencoder. But over here, it's a little bit, what can I say, a different type of convolutional autoencoder. So we put initial ensemble over here, and then we put updated ensemble by ES over here. So it is the 100 realizations. So we have 100 training data. 80 for training data and 20 for validation. Yeah, as far as I remember.
So your autoencoder is basically both forward model.
Both
update.
forward model.
No, four.
A forward model.
It's not a four.
Yeah.
It's not forward. It's not forward.
Because in order to create the output that is used in the autoencoder, you have to have run a simulation.
Yeah, ensemble smoother once.
No, yeah, but in order to run an ensemble smoother, you have to run the simulation. You're saying that the output encapsulates both kind of simulation and the simulation.
So
okay, I think I so this is created such that it can kind of replace running simulation. Right?
Yeah, it doesn't take any forward simulations anymore once it is trained.
But you're updating the coefficients in the autoencoder, right? So that is changing.
No, I don't change. Once it is trained, we don't update. Maybe, but that would be a really great idea. Maybe we can update this neural network over and over. So that's
okay. Thank you.
Let me get back to you if there are any other questions.
If we are gonna reach the break in 30 minutes, I think we need to go.
Yeah, okay, sorry.
So we get the discussion in the Slack.
Yeah.
Okay, thank you again.
Thank you. Thank you.
Got lots of good questions. People are interested.
Okay. Thank you.
And let's see.
Hello, hello.
I think
So the next speaker is Paulo Ronassi from the University of Sao Paulo. So please.
Hello all, my name is Paulo. I'm a PhD student from University of São Paulo. My advisor is Professor Márcio Sampaio, and I'm very happy to be here presenting my work. And today I will talk about deep convolutional generative adversarial networks as parameterization method in the data simulation. Here's the outline of the presentation. First, we'll make some introductions about the subject, then explain a little about the GANs, and after that, two experiments. The first, evaluating the quality of the generated members by these networks, and then its performance in the assimilation. After that, the conclusions, acknowledgements, and the references used in this presentation. So the most popular ensemble-based methods, they rely on Gaussian assumptions. So, but many parameters don't have this Gaussian distribution. For example, phase distribution or multi-level uncertainties. For example, we can have a fluid contact depth that can be multimodal. And what happens when we apply the assimilation in this kind of parameter? The assimilation vanishes its original distribution and turns it to a Gaussian one. So how to handle with this non-Gaussian behavior in these ensemble-based methods? A popular way is to apply some parameterization technique. So following this example, we have a given uncertain parameter that follows a non-Gaussian distribution. We can map it to a Gaussian field, perform the assimilation in this field, and then perform a back transform to the original field. And to do this, have several methods. For example, discrete Gaussian transform, level set, singular value decomposition. But in this work, we are focused in deep learning techniques. Some examples that apply these deep learning techniques in parameterization is, for example, autoencoder by Young-Hill, CNN-PCA, or, for example, GANs. And this recent paper performed a comparison between GANs and the autoencoders and concluded that the variational autoencoders performed better in the data simulation. However, the GAN resulted in better realizations. So the main objective of this work was proceed with the investigation of the GANs by evaluating another type of GANs, which uses an autoencoder as the discriminator. So what are GANs? It's a network structure that's composed by two networks, a generator and a discriminator. The generator takes a random vector and tries to generate samples, and the discriminator tries to classify the samples between real and fake. Real, the samples from the original set, and fake, the samples generated by the generator. And this network is trained by adversarial training, where the generator and the discriminator must compute against each other. So the discriminator is trained to better classify between the samples, between fake and real samples, and the generator is trained to fool the discriminator. Here we can see the main differences between an autoencoder and a GAN. The autoencoder uses the original input, encode it to a latent space, and then the code make a reconstructed sample. And in the GAN, the generator takes a random input, generates a given sample, and the discriminator is like a detector that tries to say if this received sample is real or fake. So now talking about deep convolutional GAN, it's like a generalization of the GANs. Today, basically all GANs uses convolutional layers. The objective of the network is like a zero-sum game between the generator and the discriminator, where we try to optimize this following min-max problem, which results in the following losses. This loss of the discriminator and the loss of the generator. And here we can see the adversarial training, where during the discriminator training, this term needs to go to 0, and during the generator training, this term needs to go to 1. So when we train one step, the other gets worse, and vice versa. Here an example of the DC GAN, the same structure as shown before, but now with convolutional layers. But this kind of GAN has several problems because this adversarial training, for example, the losses function does not have a very good shape to analyze if we are getting some kind of convergence. It is to obtain some vanishing gradients where the gradients is too low that the weights of the networks don't change anymore. And also it's very easy to obtain a thing called mode collapse. When the discriminator gets too good performance, then we only generate samples from a given part of the original set. So to mitigate this, several other GANs were being developed. One of the most famous are the Wasserstein GAN that approximates the Earth move distance or Wasserstein 1 distance. So now the discriminator is considered as critical because it don't have probabilities associated. And the critical maximize the distance between its output on real and fake samples, and the generator tries to minimize this critical output for fake samples. This is the objective, using now the Earth mover distance. And similar with the early slide, now this is the losses for the discriminator and the generator. And now, during the discriminator training, this term tends to go to 0. And in the generator training, this term tends to go to infinity, because now the output activation of the discriminator is linear, because it measures distances. So you can have values between these intervals. And because I think that I understand, called cage Lipschitz, we need to clip weights to ensure this constraint between the Wasserstein GAN, because this is an approximation. Have other methods to ensure this constraint. For example, have another Wasserstein GAN with gradient panel, but we will not see this today. And what's the differences? The discriminator has no constraint, because it needs to be a sigmoid in the DC GAN, because its output is a probability. Wedge clipping to ensure the Lipschitz constraint. And we need to pre-train the discriminator or train the discriminator and the generator at different rates. So several authors states that the Wasserstein GAN solved the training failure, however, with the cost of the convergence speed. So in this work, we are trying to apply another kind of GAN, theoretically better. We try to apply the boundary equilibrium GAN or BGAN, which uses now an autoencoder as the discriminator. So now we want to approximate the distribution of this autoencoder error instead the distribution of the samples. Authors claim that this provides stable training, and because now it's an autoencoder, I will explain better soon. Authors propose a trade-off between image quality and image diversity, and also introduced a convergence measure. Here we can see the differences. We have the same generator, but now the discriminator is an autoencoder where the decoder of the discriminator has the same shape than the generator. The only difference is that they don't share its weights. Now, mathematically, the boundary equilibrium again reaches the equilibrium when the ability of the autoencoder to autoencode the real images and to autoencode the generated images is the same. This is when the equilibrium happens. But now the discriminator has two objectives. First, autoencode the images, and beside that, distinguish between real and fake images. So authors propose that relax this equilibrium using this parameter called diversity ratio. And here we can see the effect of this parameter. For example, when we use a diversity ratio equal to 0.7, we can see more different images with some weird images like this. However, when we apply this network using a lower value, we can see more realistic faces. But for example, we can see mode collapse. For example, this face is very similar with this one, right? So here the losses, defining the pixelized loss as the norm of the difference between some input, some image, and its reconstruction by the autoencoder. Here the losses of the began, and this diversity ratio is introduced by using the proportional control, using this parameter, the proportional gain. And here the convergence measure introduced by the authors, where we can verify how the gain training is going. So first, we apply these networks and evaluate the generated images. So in this case, we use a channelized reservoir with categorical faces using this training image. We generated 10,000 of samples using this algorithm, CNSIM. We choose this size lower than other words to make the problem more challenging. For all networks, we trained until 20,000 of iterations using the TensorFlow 2.7. This was very difficult also because we cannot find any code in GitHub using this version of TensorFlow, so we need to do all from scratch. The latent space for all cases was equal to 500, and we split the faces into two channels, and the final faces obtained is the maximum value after the application of the generator. So here we can see the main differences between each network. We can see, for example, the DC gain, its loss function, don't say anything. Only analyzing this, we cannot say if it's well trained or not. The Wasserstein gain, it's like the same. And the boundary equilibrium gain, we can see this convergence. After that, we analyze the statistics of the ensemble by all networks. Here, the original dataset and some random realizations. We can see the DC-gain realization, even estimating well its statistics, they resulted in some weird realizations like this. And the vast again solve it. Here we can see more realistic channels, but we can see mode collapse. We can see that the images only generate images from a given part of the ensemble, and began get slightly better results in relation to this, and moreover resulted in good channels. We can also analyze the percentiles of the forward by the generated ensemble and the original ensemble. This is the production for 3 producers as well. I will explain about the reservoir later. But we can see this again. We can observe values very closer, the original than the generated. The Wasser again, we can see some divergence. And the boundary equilibrium again, few better results. And now, performing the simulation, we have 2 options. The first, we can start by encoding the original ensemble to obtain an initial latent space ensemble, like this working. But we can also start our algorithm simple by generating an ensemble from a random multivariate distribution. Here are the differences between the 2 methods. First, we have the initial ensemble generated by the machine. And we need here, the difficulty is because we need to train another network, we need to train an encoder using the generator as the coder, but freezing the weights of the generator. So we need to train one more network, and then we perform the assimilation loop using an iterative method. And by the random, we simply start generating these vectors, and we generate the initial ensemble by passing this random by the generator. We applied this in this following reservoir. This reservoir contains 51 blocks. This is the reference model. It contains 9 wells, 6 producers, and 3 injectors. These are the producers, and these the injectors. Then the measurements was the oil and water production rates and the water injection rates. The amount of data is about 1,000. It's monthly measurements. The one parameter that was assimilated was the log variability. For our case, we used an ensemble equal to 200. And the data simulation algorithm that we used was the ensemble smoother with multiple data simulation with constant iterations and constant inflation factors. Briefly speaking, here is the ESMBA update stat, where we have here for each ensemble member, we have the prior ensemble member, CMD and CDD are the covariances, the cross covariance between M and D, and the out covariance between D. CD is the covariance of measurement errors. Alpha is a parameter called inflation factor that bends each iteration that must follow this rule. And also here is the measurements, the output of the simulator. And in this method, the measurements must be treated as random variables also. Now the results. First, by the method starting by encoding the initial ensemble, we can see that resulted in some false connections here. The Wasserstein again resulted in like this and began this, but we used relatively few members to train the network, so this was expected. Here the objective function, this objective function is the difference between the simulator data and the measurements normalized by the covariance of measurement errors. We can, here it's in logarithm scale, so we can see a good reduction. Now start by the random samples. We can see good results here for the DC gun. Wasserstein gun fails to match here one channel, and the gun gives similar channels. And also the objective function reduced significantly. Here the time series for producer rel 2 and producer rel 4. Here's our rate. The gray lines represent the forward from the prior ensemble, blue lines from the posterior ensemble, and the red dots is the measurements. We can see some divergences here and here, for example. And in the case that we started by the random samples, these results were better. In exception of the case with the Wasserstein gun. But we are interested in the big gun because the shape of the convergence of the loss functions. So what we can conclude? The big gun resulted in stable training because it's convergence. Generated images without continuous, with the ensemble mean and standard deviation closer to the original ensemble in comparison with the Wasserstein gun, and provided equivalent simulation results. What we can improve now? We might evaluate the effect of these hyperparameters in the problem. Also analyze different big gun architectures, for example, this one, big gun E. Big gun E because it uses an ensemble of discriminators to classify. The parameterization and generation of three-dimensional reservoir with guns is still an open problem. Here the references used in this word. So thank you for your attention.
Maybe I can start with one. I think in some of the experiments, the spread of the production profiles seems a little bit low.
Yeah.
Doesn't mean that the manufacturing have problem of random traps, you know.
Started to apply localization in the latent phase.
Yeah.
But I omitted here because the time.
So you don't use localization.
Yeah.
In this case. Okay.
No, in this case, no.
No.
But I'm starting to apply it.
Yeah.
Maybe I can ask one. You said the generalizations, the 3D is still an open problem.
Yeah.
What do you think has to be done to be able to make it?
In my opinion, I need to test it, but I don't know. Maybe if the network is passed by a good training, we can make it like a layer by layer. And I don't know if this generative model can generate, for example, any layer of the reservoir. Or I think it's more difficult, use three-dimensional convolutions.
Do you think you need to increase the number of ensemble members then to be able to get a good representations of the concept? Because then it will be time consuming.
Yeah. Here I try to use less just because that.
Yeah.
I don't know. because for example, 8,000 of members, it's infeasible for real case.
No, it can be difficult.
Yeah, so I don't know if you can, for example, with 500, we can generate realistic samples. It's not to be tested. But we try to use this structure just because that if you are working with a harder problem, this cannot give to us any information.
Yeah. Okay. Any more?
Yeah, sorry. Probably just a very, very stupid question. I missed maybe the motivation. So this is a something magic, is it? So,
Something metal? What, the assimilation?
no, I mean, you train this adversarial neural network,
Yeah.
right? In order to obtain a starting example, right? Or you are assimilating as well? Because I missed the part where
I'm assimilating the latent space. Why? Because if I assimilate, for example, this ensemble,
yeah,
the data simulation method will map all of this binary distribution to a Gaussian one. If I don't use any truncation, but the main motivation is to map this binary distribution to a Gaussian one to make possible the application of the ensemble-based methods in this Gaussian. I don't know if you...
Yeah, maybe we will talk a little bit later.
Okay.
Yeah, thank you.
Thank you.
Yeah, if it's no more questions, then we are done. Then. Thank you.
Thank you. Yeah. Now I'm trying. I will try to apply this modality again to a bigger case. No. I don't think
he has done something similar.
Yeah, he applied this again, but he applied another. He applied this again, and another kind of games. But no one using this auto encoder.
Oh, okay, so it's a different type
Yeah. The convergence of these standard guns don't say them. So my fear is when I will apply that a big case, I never will know if these guns trained or not.
Yeah, but you could maybe start out with some simple cube or something.
Yeah.
But because the problem might be that the classes, they are also they are not different, they're correlated, they're separate. So they are objects.
But
maybe it's possible to recognize objects.
But I think if my network is really good training, make the simulation can detect this vertical correlation.
Yeah, it could maybe detect that, but I'm just worried that you might need many samples.
Yeah.
Because you have so many.
Yeah, but what I'm thinking, for example, if I have 3-dimensional reservoir with 30 layers, I can use each layer to train the
Yes, but you're not lose some of the correlation.
Yeah, but this is my point. The assimilation cannot get this correlation even with 2-dimensional networks. I don't know. I need to check.
Yeah. Maybe you need some 3-dimensional. Maybe it's possible also.
Because if we can do that, for example, if I have 20 layers, I can multiply my sample by 20 and use each layer as a unique sample.
It could be.
But I don't know, I need to test.
But that would be very interesting to see if it's possible to go for
The main problem is that I cannot have a large scale reservoir to apply this. I have the Unisync tube, but I applied the SMDA without parameterization. I faced some convergence issues in the model, so I don't know if I can.
Okay. You have this Bruges model. That's
Bruges has faxes also. I will check. I will check it. Bruges. Because my page purpose is to assimilate these kind of faces. So I need first decide the parameterization method and see how the adaptive localization works inside with it.
And so you probably need to apply something
Yeah.
for the same.
Our motivation to develop the localization method in collaboration with Sheldon was because of this, to apply this localization in the latent space. Because if we see the results, we can see for all cases the ensemble collapse. Even he matching the channel, it's collapsed.
So you have but you have a lot of data.
I generated this data synthetically. Yeah.
So,
The ratio between the ensemble and the data.
why do you think it collapsed?
Because the standard deviation of the posterior models.
But why do you think that happened?
I think I need to invest. I don't know if it's because I don't use any localization or the size of the latent space.
一国，
Maybe reduce.
你要不要跟那个 speaker 的你因为那个第一个是那个 Hamza， 他现在在那里，你问他要不要那个还是怎么样？对，你可以问他一下，你说要不要现在试一下，万一有啥问题。然后我估计联系他去试一下。对，你在那边，你估计待会儿他讲的，你也把它关，会有那个回音。就是说你可能坐在这边比較好，然後我拿到話筒到後面。然後第二個他那個在這裡，我知道。You are the second one. I have opened your file. I have opened your file. So this is the one.
Yeah. Perfect.
Yeah.
Perfect.
Good. Yes.
And I need to implement everything from scratch, so it takes a lot of time.
You explained it was very good that you spent some time in the beginning because perfect is that you only understand 10%. So you need to explain things to them.
Thank you.
Okay.
We'll be leaving some
Okay, yeah. So you go back to see you next time.
Hi Hamza. Can you hear me? Do you?
Yes, I can hear you. Yeah.
Okay. Yeah, good. Can you try to share your screen and yeah, before start? The song seems good. So.
Okay, good. But on my side, actually, it's the sound is not very clear.
Yeah, I can see your screen right now.
Okay, good.
Yeah, it looks fine. Yeah, I think it's perfect. I can see your screen. Yeah, full screen. Yes.
Okay, good.
Looks good. Yeah. Thank you. I will try to text you when 10 minutes left. And if you cannot see that, it doesn't matter much. I will, yeah.
Thank you. Appreciate that.
Yeah, people are coming back, so we will start soon.
Okay, let me start my video.
I mean, you can go back your one slide back to your
Oh, yes.
title.
Yeah.
Yep, that's perfect. Maybe let's start again. The next talk is from Hamza Huizai-Kak from King Abdallah University of Science and Technology. The floor is yours. You can start. Yeah.
Thank you so much. Thanks for giving me the opportunity to present on this nice workshop. So I want to make sure everybody can hear me very well.
Yes, we can hear you well. Yeah.
All right. So this is work joint with Dan Crisan from Imperial College London, Pierre Del Moral from Andrea Bordiux, and Ajay Jasra from KAUST. The talk today will be about estimating the normalizing constant of the data likelihood associated with the Kalman-Busi filter, and then use this estimator in parameter estimation in high dimensional models. So this is the outline. I will give a background about Kalman-Busi filter, and then why we need to use ensemble Kalman-Busi filter. And of course, we will have to discretize in continuous time, and then compute the normalizing constant of the data likelihood and provide an estimator of the normalizing constant, and then show some theoretical results related to conditional bias results and ln error of the estimator. Then I will describe how we use this in static parameter estimation and show some numerical examples. So let's consider this state space model. You have a hidden process, xt, that's given through this SDE. And you have another process, it's called the observation or data. It's given also through an SDE. A here is a matrix, Q and R, Q1/2 and R1/2 are symmetric, positive definite matrices, and C is can be anything. So the idea is to approximate or estimate the filter distribution associated with this filtering problem. So in this case, because we have a linear and Gaussian model, the filtering distribution A to T is in fact Gaussian distribution as well. And it has a mean and covariance matrix. The mean is the expectation of xt, the process at time t, given a filtration of the data up to time t. So you can say, given the data up to time t. And the covariance matrix is just defined like this. Now, the mean of the filter is actually given by this equation, the Kalman-Busi equation, as we can see here. And P, the covariance matrix, is given through the Riccati equation, which is defined here. S here is in blue is just C transpose R inverse C. The problem with this is sometimes it's really hard to solve these two equations, and if it's possible and we can solve them, then it will be very expensive. It will be in the order d squared, where d is the dimension of the state xt. So what we need to do is to consider conditional nonlinear McCain-Vlasov type diffusion process xt, and it's given by three different forms. The first form here, it's associated with the so-called vanilla EnKF, where we see here that we have two sources of error, DWT and DVT. And we have here, this is covariance operator. It's a function of the filter distribution. The second one is called deterministic EnKF. It's not actually fully deterministic because you see here that we have DWT. And of course here we get rid of that and replace when we have this extra term. The third one is fully deterministic, so it's called deterministic transport EnKF. So as you can see, we don't have any source of noise here. Have to there's of course we have to be careful when computing this inverse. So WTVT and X0 are independent copies of the Brownian motion WTVT and the initial value X0. And this, as I said, P eta T is the covariance, which depends on the filter distribution. So eta T, again, it's the filter distribution, as you see, it's defined here. And EX is just X. So if you substitute that here, then you get the covariance matrix. So we have this famous lemma that if xt in any of these three versions is such that the expectation of x0 squared less than infinity, then we have the filter of the Kalman-Busi in the previous slide is actually equal to the law of xt bar given the data, which is also, as I said, it's equal to the xt in the previous slide, given the law of the xt given the data. However, one cannot compute this covariance exactly, so we need to use the ensemble Kalman-Busi filter, which we define as following. We have n samples, and so we approximate the covariance by taking the empirical measure as follows. This is just the delta Dirac function centered at the samples xi, ti. Then the sample mean, we define it to be mtn, just the average of the samples. And of course, then we compute the samples covariance, which is like that. So we get a matrix that depends on mtn. So for more details on this and some supporting theory, here's two papers by Bishop and Del Moral and Togart on the stability and uniform propagation of KS for this kind of Kalman-Busi filter. Now, since we don't have actually access to the entire trajectory of observations, we need to work with time discretization. So we discretize these three versions by taking a step size of delta L2 to minus L, where L is the level of discretization. It's an integer. Then we define the Euler version of the three variants: the vanilla EnKF, and deterministic EnKF, and the deterministic transport EnKF. Okay, so now computing the normalizing constant or the data likelihood. So consider that we have two functions f and g. F is defined on the path space of x, and g is defined on the path space of y. Then the expectation with respect to the law of the pair xy of f of x from 0 to t times g of y from 0 to t times some constant inverse is equal to the law of the pair xw, where w is the Brownian motion in the x process, and expectation of fx from 0 to time t, g of w from 0 to time t. And we can do that using Garzanov theorem, and this the normalizing constant here, it can be or this constant can be defined as follows. One can prove that. So then we can introduce a new probability measure p tilde, and then take the radon-Nikodym derivative with respect to p to be actually this ZTXY inverse. Then using Calember-Strebel formula, we have that the expectation of f of x s s from 0 to t, given the data up to time t with respect to the measure p, is equal this ratio, where you have the expectation here with respect to the measure p tilde. So now, since we'll be given the data up to time t, then we can fix the observation process and then define the likelihood function of the data to be the expectation of this function ZTXY with y fixed. So this is actually will be the normalizing constant of the data likelihood that we want to compute and then estimate. Okay, so here I will show you how we compute that normalizing constant very quick. So here's the normalizing constant. Let's define it to be exponential of qt. So this integral here is qt. Then we have dztxy is equal to partial qt of this function, partial qt plus 1/2 partial square of partial qt square of exponential qt partial square qt. So just using Eto's formula, and then we have this term for the first term here, and we have this term for the second term here. And as you can see, this term will cancel with this term, and we have dztxy equal ztxy times this inner product. Then integrate, and you have 1 when the time equals 0 plus the integral of zs xy times the inner product here. Now take the expectation with respect when the y is fixed on both sides. So taking the expectation here will give us zt y, sorry, which is equal to 1 plus the integral of the expectation of this thing here with respect to y, which is here. But now multiply by this and divide by it, which is equal to 1. Then this guy here, sorry. Then this here is the definition of then this is the expectation. Let me see. This expectation is yes. Yeah. So yes, this will give us dz txy, which is which is this guy here. Now, so from this equation, we have that doing E2 formula again. So take the derivative of this guy, then you will have, and then take integral back. Then you will have this is the normalizing constant. So let me remind you what's ms here. M is the mean of the exact mean of the filter, and S is C transpose R inverse C. So this is the normalizing constant of the data likelihood. Now, a natural estimator of the normalizing constant is to replace ms by the sample mean, MSN from the ensemble. So we replace ms by MSN. And of course, in practice, we have to discretize this integral. So we have this estimator here. And in practice, again, we actually need the log of this guy. So we define the log of this to be UTNLY. So this is what we care about, and we'll use in parameter estimations. Okay, so I'll show some theoretical results. So first we'll start with conditional bias results. So let's define this conditional this conditional expectation of empty end and simple mean given the data up to time t, and we have the expectation of the covariance matrix from the ensamples given the data up to time t. And let's recall that the vanilla and the deterministic EnKF, they look like this. Then we have the following theorem. So if we consider these two cases, and the assumption one, which was in the previous slides, or okay, so assumption one is okay. Assumption one is here. It's in yellow. Assumption one is that S, which is C transpose R inverse C, is equal to the largest eigenvalue of S plus S transpose divided by 2 times an identity. So if we assume that, and we assume it's greater than 0, and also that the largest eigenvalue of A plus A transpose divided by 1/2 is less than 0, then for any n greater than or equal to 1, and the number of samples sufficiently large, we have that the expectation of MTN minus MT power n all to the power 1 over n is less than or equal some constant divided by n, when this constant doesn't depend on the number of samples. All right. So this is a like kind of LN error theory. The second conditional bias result is for the log normalizing constant. So this was for the sample mean. Now we're gonna introduce another result for the log normalizing constant, which is UTN. So let's define this conditional expectation of UTN to be UTN hat, where again, remember that UTN is the log of the normalizing constant. Then we have that the difference between UTN and UT, which is the exact log of the normalizing constant, is like this. And this can be written as two integrals. Now take the expectation of this given the filtration up to time t. Then you have C, you have here, you replace MSN by MSN hat. And here you have the expectation of all this. So let's call this alpha t, and this is beta t. Then we show that in the cases 1 and 2, the vanilla EnKF and the deterministic EnKF, that the expectation of alpha Tn to the power 1 over n is less than or equal some constant square root of t over n. And that for beta, we have Cn t over n. So here's square root of t, here's t over n. Then we have the following two corollaries. Consider the cases vanilla and deterministic, EnKF, and assume the same assumption in the previous theorem. Then for any n greater than or equal to 1 and t greater than or equal to 0, and n sufficiently large, we have the ln error of the conditional bias is less than or equal some constant times t plus square root of t over n. And this c doesn't depend on t or n. And for the third version, which is the fully deterministic transport EnKBF, we have that the expectation or the ln error of the conditional bias of the log normalizing constant is less than or equal c over n. So you see here no dependence on t, and that's because this is fully deterministic. And also we have ln error. So this is different from the previous slide. This slide, so we have UT hat. This is UT hat. This is the conditional bias here, or the conditional expectation of the log normalizing constant. This is conditional expectation log normalizing constant. Here we have actually the log normalizing constant estimator. So the log normalizing constant estimator minus the exact log normalizing constant. So we have in the case of 1 and 2, this result. So we have this bound on the ln error, and in the fully deterministic case, we have this bound. Again, we don't have t here because this is fully deterministic, and actually t in these cases comes from the noise W and V. All right. Now I will quickly describe how to use that in static parameter estimation. So now let's assume that we have theta in our state belongs to RD theta. So these parameters are static and unknown, and they can be in the in the X process or in the Y process. And we use a recursive maximum likelihood method to update theta. So you see here that we need to compute this guy or estimate the difference between the log of the normalizing constant at time t and at given at theta. Actually, this should be theta t minus 1. minus log at time t-1 theta t-1. Now, we need, of course, to estimate the gradient of this difference. So one way is to use finite difference, but the finite difference will require 2 times d theta calculations, while in this methods called stochastic perturbation or simultaneous stochastic perturbation, simultaneous stochastic perturbation approximation, SPSA, we have only 2 computations, where in fact you have to perturb theta k at a random direction for each k from 1 up to time d theta. And here I show some numerical examples. So let's consider a linear model that I showed at the beginning, linear Gaussian model. And let's take the dimension to be 100. So the dimension of the hidden state is 100, the dimension of the data is 100. And let's assume that A is some parameter theta1 times the identity, and that R1/2 is theta2 times some matrix R, and C is a uniform random matrix. R2 is the identity matrix times 2. So then we use the normalizing constant estimator coming from the F1 case, which is the vanilla EnKF. And as you can see here, it converges after 20,000 steps to the parameters. And this is using the second version, which is the deterministic EnKF. It also converges and also using the fully deterministic. And as you can see in the fully deterministic, the variance is very small. And that's because it's fully deterministic, no errors or noise. The second model is to the Lawrence 96 model. So Lawrence 96 model is you have this function now. It's not linear. So you have a nonlinear function here. Of course, the filter will not be optimal for this problem, but people use the EnKF in these cases, and it shows that it's working. So this f is defined like this. It's xti plus 1. I here is the coordinate. So we have 40, the dimension is 40. So this is I plus 1 minus xti minus 2 times xti minus 1 minus xti plus some unknown parameter. Theta here is the external force in the system. And the first term here is the advection-like term, and the minus xt is the damping term. And the true value is 8. And as we can see, using the 3 versions that and the normalizing constant estimator that we have a convergence very quick to the true value. All right, I end my talk here, and apologize, I ran out over time by 1 minute. So
thank you.
Any questions? No? Online, no question online, Mr. Yes. Yeah. Then we move on, or?
We can wait a bit until if we should take any part otherwise, I'm sorry.
maybe we can move on, no? If no questions. Thank you very much. Yeah.
Thank you, everybody. Thanks.
Could you stop sharing and share my screen? You know. This one. Share it. Not put the view in full screen. Just this one's working on. Yeah. Yeah. Maybe there's a pointer as well. All right, we move on to the next speaker, Sebastian Tel from ET Berlin. Yeah, please, the floor is yours.
Thank you. Okay, so yeah, thanks for the introduction, and also thanks for the organizers for yeah, organizing this nice workshop and for giving me the opportunity to present some of my research. So yeah, what I'm talking about is joint research with my supervisor, Wilhelm Stammert, who's also at TU Berlin, not so surprisingly. And okay, before I start, I should preface that with saying, well, we both did numerics at some point in our lives, but unfortunately that point was not when we did the paper. So the paper itself is mostly on the basic analysis for EnKF, so showing existence, uniqueness results, and converges to the mean field limit. But sort of instead of torturing you with proofs and abstract theory, what I'm presenting is more of, well, let's say, the best parts of it. Hopefully that may also be interesting to more practically minded people. Okay, so as usual, the first few slides are just there to get on the same page. So just as in the talk by Hansa, I'm looking at the continuous time framework because I like to work with differential equations. And yeah, I'm actually, that's a bit different. I'm looking at this correlated noise framework, it's called. You find that, for example, in this book by being example. So a signal in this case is this SDE with two different noise terms written up in a special way. Although it doesn't matter that for most parts of the talk, it doesn't matter that it has this form. That's more convenient for the proofs actually. Later on, you could just write sort of the same noise term in both the signal and the observation, and then use projections to differentiate. Okay, and you can greatly, of course, then the goal of filtering is to complete this posterior, and you can greatly generalize most of the assumptions that we have implicitly taken here with this form. So I'm mostly making these assumptions like sort of non-homogeneity, so homogeneity and sort of linear observations, for example, and uncolored observation noise, mostly for convenience and notational brevity. Okay, then as I said, the goal of filtering is classically to compute this posterior, which will be denoted by eta. And one way to do this, as you know, at least in the linear Gaussian case, is to use the ensemble-Kalman filter, or in the continuous time version, it's called the EnKF. So that's for me, just to get ourselves on the same page. In the uncorrelated case, which we look at here, that's this system here, this particle system, where of course this I varies between I and M, between 1 and M. So the number of particles will be fixed at M. And the way it sort of achieves its goal of approximating the posterior is basically, right, it's a particle system that approximates this mean field system. We will also call the systems Makin-Vlasov equations, so stochastic differential equations which depend on the distribution here through its mean and covariance. And actually, you can show, actually we will do this later on also, that the posterior distribution has exactly the same marginals as the process defined by this equation here. Okay, and in that sense, sort of the EnKF is in the mean field limit consistent with the true posterior. But the way I've written it up, of course, is already in a non-linear way, and well, that's not consistent. It will be motivating. Hopefully, we find some slight motivations why it still makes sense to look at this in a non-linear case later on. Okay, but first, what we want to do, actually, we want to, so the overall goal will be to derive ensemble common DC filter for this correlated noise framework. And we'll do much more. We will now sort of find consistent representations of the posterior free mean field equations. Okay, so basically, if you in mathematics, usually if you want to know why something works, it's good to sort of look at it at a more abstract level or more high level, so that you can generalize this to other situations. So what is happening? Basically, it's just two steps. First, we derive the mean field process, which is consistent, meaning that its law, which will later on always denote by either bar, the mean field process will always be called X bar, is the same as the posterior, which we see. And in the second step, and this is the step which probably is more interesting to you, but I will not be focusing on it that much, then you approximate this mean field system by some particle system. You approximate this X bar by some particle system, which is then in the linear case system in EnKF. Okay. And now the question is, of course, how do we find such an X bar? That's sort of the main problem. And the solution to this is a classical equation from filtering, which is this Kushner-Sakai equation or Kushner-Sakai equation, which exactly describes the evolution of the posterior. Okay, so we will see it in the next slide. So don't worry if you are not that familiar with it. Okay, and I should just in honor of the people who came before, I should say that we basically follow the guidelines that were put out by this paper by Patricia, Reich, and Stannard for the uncorrelated case. They unified a couple of quite well-known consistent nonlinear filters, specifically, for example, the feedback particle filter here, or also this filter by Krishan and Xiong, and put them in a unifying framework. And actually can also, if you just like their work more for whatever reason, you can also look at this paper by Nüsten, Reich, and Osler, where they also do this for the correlated noise framework. They arrive at it in a slightly different way and also have some slightly different interpretations. Okay, so here's the Kushner-Sakai equation. Actually, I've written it in a weak form now. Doesn't really matter. Just to say, because this will appear later on. So either evaluate that H will always be the sort of mean of H with respect to either. Okay, this will appear later on. And this is a benign-looking stochastic differential equation. Its concrete form doesn't really matter. The point is what you have here. It has two terms. One is this generator basically of our signal process, so the signal process that appears in it directly, and that's perturbed by this non-local, non-linear term, which is a result of the conditioning. Okay. And okay, so I've written this. I should have probably written it in a strong form, but maybe that is a more classical form of stochastic partial differential equation. But anyway, so what you see then is, because of the non-locality, what is very natural, is to consider McKean-Vlasov processes. Okay, so what we want to do is we want to find a process such that its law evolves exactly according to this equation. And due to the non-locality, well, that's a property of these McKean-Vlasov processes, of these McKean-Vlasov equations. Okay, that's just some motivation. If you're not familiar with the framework, this doesn't matter. Just let me tell you that this choice here, so this ansatz here for finding this process, this stochastic differential equation, is very natural if you know your stochastic analysis well enough. If you know about these McKean-Vlasov equations, you see these dependence on the law in there. That's what makes it a McKean-Vlasov equation, and they have exactly this property that we see. Okay, and what you see again is the splitting up, just like in the Kushner-Sakai equation, into two parts. First, the signal, and then it's perturbed by basically just two terms, one term of finite variation and one term of the signal that's also mine. What we will get out of this is that what was before called deterministic ensemble Kalman user filter, that's also my interpretation, that it's basically a deterministic perturbation of the ensemble. If you think that this Y, that the data stream that you have, the observations, you usually often just make observations once, right? So it's sort of deterministic. Okay, this was unnecessary, but mostly. So we make this ansatz, and now it's basically just about finding this K and finding this A. So how do we choose this A and this K? So it's unnecessary, completely unnecessary. So okay, as I said, we have a process. We want to find a process which, such that its law, either bar, actually evolves according to the cosine autonomy equation. Okay, but by the choice that we made before, which was this McPherson-Glasgow equation, we already know how its law evolves, which is this Fokker-Planck equation. Yeah, that's actually written in strong form. I shouldn't have written it. I should have written the Cosine autonomy equation also in strong form. Sorry about that. Because originally, in my original presentation, I did everything weak. Okay, the only point is now that you make a comparison of the coefficients. Okay, what you see here is basically that here you have this K. Here you have minus the divergence of either times K. This must exactly be equal to this term here. By that, you see already here you have also some divergence here, and that's the only part where there's this correlation in the noise, where this C tilde comes in. So basically, going from the correlated noise from the uncorrelated noise framework to the correlated noise framework is super easy in terms of the gain, we'll call it, as you will see later on why. You just make a translation, okay? So it just translates the gain term in the uncorrelated case by this constant C tilde. Okay, so that's easy. And this K0 must then adhere to this partial differential equation. That's not unique, of course, because the kernel of this thing here is non-empty of this differential operator. So you have some freedom of choice. And these filters, these classical consistent filters, they basically come from here by making some choice on K0. So for example, if you choose K0 to be of gradient type, that's the feedback particle filter. Okay. But in this form, okay, now we know what the correlation in noise does, but I think from this picture it's not quite clear maybe what K0 actually is. So there are different ways to interpret this. My interpretation is sort of a kinetic one, and for this it's quite useful to go to the flux form. So we write this equation here in flux form. So for any arbitrary domain D, you can write this before by integration by parts simply in this form. And what you will see here on the left-hand side, that's the flux. And so for particles, think about this in a kinetic way. You have particles that are distributed according to either, right? Which is what we want to have. So then the thing on the left-hand side is just the total flux of those particles into the domain D, because we have a minus here of the orthonormal, when they are moving with speed K0, okay? And on the right-hand side, here is the difference between the observation in D, the average observation in D, and the global average observation. So in other words, it's sort of, okay, and the speed K0 is chosen such that these two things are equal. So in other words, K is sort of an exploration velocity system in that direction. So this K will always push those particles into those regions where you expect most of the difference between the observation you make there and the global average of the observation. So where you have most, where the observations deviate the most from the sort of ensemble. Okay, and this kinetic interpretation will be quite useful later on if you see the full term. So okay, then we also have to treat this A. Don't care about all this nonsense, it's far too much. We will go through it actually later on a bit. But the point is here, as you see here, this A is basically already determined by K. That's the only point of that's what you should get from this slide. Up to, again, you have some perturbation by this ether harmonic, we call them ether harmonic fields, so the elements of the kernel of this divergence operator. Okay, and then the whole equation looks like this. You can also write this term here, which appeared in the A, also as a logarithmic derivative. And then you see some similarities. So just as the EnKF, this X bar basically takes the signal. Then we perturb it. Now you see already why K is called the gain term, just as in the ensemble common UC filter. It just incorporates this innovation term here. And you see what we had before, right? This is the deterministic ensemble common UC filter, which you get basically because of the answer we made. You see actually that this innovation term is universal. You don't have much choice how to choose this innovation term. And then I skipped this term at first. So then this part here, that's the only way where these correlations appear again. So the correlated noise appears again. That's basically just results in an inflation term, right? So in this logarithmic gradient of the log density. And of course, as usual, you could replace it also by another Brownian motion, by another noise term. Okay, and then that's the difference between the ensemble common filter in the form. We have this correction term. Okay, now that's written up uglily because K is a matrix, but think about the one-dimensional observation case. Then K is a vector, and then this thing here just reduces to the advective derivative. So exactly the nonlinearity in the Navier-Stokes equation. That's, if you don't know what it is, why this appears also there. It's the change of the particles of sort of the field K under a flow that moves with velocity K. So again, here the sort of kinetic interpretation I think is useful to interpret this thing. Okay, so as I said, you can get a bunch of nonlinear filters out of it, and you can also get the EnKF out of it. That's the main part. Namely, if we assume that either is Gaussian, then one choice of K0, again, remember we have a choice, is actually the common gain that you know, right? These covariants, and this also holds for nonlinear observations. So I just had this for simplicity, and you get this out. And I should say, to give the right credit, actually this is not surprising because as soon as you know you get the feedback particle filter, that was sort of the main thing of the feedback particle filter, that it was a true generalization of the EnKF. Okay, and here we have these inflation term, and in this paper by Nüsten, Reich, and Rostever, they also get these, of course, but they are more numerics people, so because these, of course, this inverse can be a bit tricky, and the gradient of the logarithmic density can be a bit tricky, they replace it by noise term. Okay, so okay, so now just quickly, I've written it here up for nonlinear systems already, which for nonlinear signals, which is of course wrong, but the question is, can we motivate this somehow? And the answer to this is yes, because of some nice universal property of K0, namely, you can show quite easily, surprisingly, by integration like parts, that the mean of your common gain is exactly this covariance term, right? This was this P bar I called it before. So exactly the common gain that you have in the classical ensemble common UC filter. And now you can think of this, I mean, here I've written some ways I think that's far too fancy, but if you want to be fancy, you can say, well, the EnKF, how it relates to sort of the consistent way, the consistent filter is basically that it's a universal, because it doesn't matter how we choose our K0, a universal zero order approximation with different expansions, right, where the zero order terms are always the mean. So Kahun-Löwe would be one example. Much more important, I think, would be these polynomial projections. So because those are the things that you need if you want to get moments, right? And yes, so that was the justification in the non-Gaussian case. Then, okay, this equation here, from now on, we are actually a bit closer to the paper. I don't know how I'm doing time-wise. I should have some time. Okay, now we get closer to the paper. Actually, this equation looks benign, but it really isn't. So actually, what you see is you have some Lipschitz, local Lipschitz. So local Lipschitz condition only. Even if you have C tilde 0, then this P inverse can appear here. Even then, you have just local Lipschitz. So you have Pn times x bar, P bar times x bar. The problem is there is no, unlike for normal stochastic differential equations, there is no general proof for existence of McKean-Glasov equation on the local Lipschitz conditions. And you can even get counterexamples. So that's very nice work by Scheutzer here. And so basically the paper, the main part of the paper is devoted to making the proof here. And of course, non-uniqueness would be bad somehow in practice. If we really go to the large particle limits, then we would be able to guarantee that it converges against the right thing. We are able to prove this. There are also people who prove this for other results. Actually, quite nicely, it relates to the talk before here. For linear signals, because you are consistent and the p bars, so the covariance decouples by the Kalman-Busse equation, you can actually make a very easy fixed point argument, very nice, which was part of the paper that was presented before. Then there is some work by Kogi, where they had to assume that H is bounded, which is not so nice. We were able to prove it for linear H. That was one part, main part of our work, where we had to do a lot. I will not talk about the proof in any shape or form. Just maybe what could be somewhat interesting to more practically minded audience. So okay, basically we have this condition here that the minimal eigenvalue of this noise term has to be greater than 0, basically because we want to keep our covariance matrix regular. If you're dealing with the uncorrelated case, this wouldn't matter at all. But because in the correlated noise framework we have this P inverse, we want to keep it regular. And the main working horse, some form or the other, are the spectral bounds for the spectrum of P bar, which we denote always by lambda, that you derive. Yeah, well, we'll come to the end quite soon. So yeah, so as you can see, if we require this, then here you see you are always your spectrum will be always bounded away from 0 uniformly. You can get uniform bounds out of this. Especially a nice property is that you have a minus in front of the lambda squared always here by the upper bound, so it drives you back. Okay, then yeah, this was just some remarks which are not that important. Then of course you can write down the approximating particle system, which is naturally given by basically basic statistics, right? You replace the true moments that we have by the empirical ones in this interacting particle system as usual. And okay, here you see already why you might want to actually want to replace this inflation term by noise, as Osterman did, because this thing here is not actually this thing here. So the pseudo inverse it is times the center particle that develops singularities. You can show this, and we found this interesting because what is not so good numerically can be quite interesting sort of for theoretical mathematics. We actually showed, that was another main part of the paper, by this generalization of the thing we had before, of this condition we had before. If you already start with something regular, I will come to that in a minute, or in a second, I should say. If you start with something regular, you stay regular. It's much harder than in the mean field limit to prove this, because now you don't have a differentiable decomposition of the spectrum in spectral decomposition. So we had to work with the matrices all the times, and it was horrible. And you have, okay, this condition here, this takes care of the fluctuations of the covariance matrix, that's what it is. And this assumption here that Pm0 is regular, which implies, of course, that your ensemble size is strictly bigger than your dimension. This is basically just in technical assumptions because the equations to deal with are very, very ugly, very long, and we wanted to make this, cut this down, and this helps actually to cut these things down and make it a bit simpler. Okay, then will not go through this. You can, there's an ancient paper, I'm not quite sure whether this, the practitioners know this, some of the mathematicians didn't. It's an ancient paper by Kubancic, I think, which sort of gives a recursive formula for pseudo-inverses of exactly these covariance matrices, which allows you to, at least in theory, give you something which computes in linear time, linear complexity with the dimension, these terms. Okay, and finally, we have a very weak, weak propagation of chaos results, very weak mean field limit result, weak in the sense that we get implicit rates where we bound the implicit rates are given in the sense that we have to first stop always when the covariance matrix gets too large or it gets too singular, and then we get the rates that we want. Then we get exactly the rates which you would expect from a law of large numbers. And this gives you a convergence improbability, at least, by some arguments, but it doesn't give you more. Okay, so then I have finished, I think. Actually, sorry. So, yeah, set my timer, and yeah, I'm very looking forward to questions. And here are some references I used.
Any questions for the
That's a great talk. So like, I just want to make sure. So like, at some point you mentioned that the ensemble common aberration filter is a zero order approximation of your like equation. So does that mean that
okay, this is a bit, it was a bit vague. So what I mean by zero order, means, right, we approximate the true common gain that you need by something which is of zero order in different expansions that we could use.
Yeah, so does it mean that in the linear Gaussian case, you just recover the...
Yeah, in the linear, yeah, exactly. In the linear Gaussian case, you can basically, one solution that you can use for this K0 is exactly this thing here. You can also get other sort of solutions in the Gaussian case, actually. That's what this filter by Krishan and Xiong gives you in dimension d greater than 1, strictly greater than 1. Yeah, in sort of so if you will, a mass property, if you will, for this with this kinetic interpretation of this K as a speed. For Gaussian processes, it's possible to choose it basically constant. And every distribution where you could choose such a speed constant, velocity constant, well, there you would be able to use the ensemble common filter, basically.
Cool. And then another question. So do you have like a convergence to equivalent proofs for your system, stochastic system?
What do you mean by convert? So ergodicity, so convergence to something stationary? Or
Yeah.
No, we haven't looked at it.
But you have a mean field convergence.
Yeah, we have a mean field convergence. We mostly, the project mostly started because of what I put here shortly, because of this thing here that you don't have this unifying framework for existent results for McKean-Vlasov equations. Both me and my supervisor are very interested in that, and that's why we mostly focused on the mean field system originally. Actually, that's what it is.
Laura?
Want to be sure you're considering time correlated observation errors? Spatially correlated? Or
No. So the correlation basically just comes in your. Well, if you have a discretization, then wait a second. So if you think about this as a discretization, right? The correlation basically comes in that you have sort of the same noise term here.
Okay. Then there may be special cases that would simplify the problem. For example, when the correlation is autoregressive of order 1, you can consider the increments and be back to the normal case. I don't know if that may help
Okay.
in some mysterious way.
Okay. Oh, thank you, thank you. Yeah, I have to say for us, I mean, the talk, I know the title is named, puts the correlation more in the center. For us, this was more a tool just to show the power sort of our method in the analysis, that we also can reach this space. But yeah, it's very interesting. Thank you. Yes. Yeah.
Oh yeah, Patrick has a question.
Sorry. So I didn't get anything from this.
Okay.
But let me see if I got something.
Okay.
So come obviously is complicated because time goes, delta t goes to 0. And you also have stochasticity, and you're considering particle flow rather than just common filter or just a true base, perhaps. So, and then you show existence or convergence of curve.
Yeah, the main main part of this paper is showing existence of this equation that we have here, which existence, uniqueness, and basic analytic properties of this equation which we have here, which is not covered by mathematical literature, existing mathematical literature. All
right. So any questions?
Oh, yeah. Thank you.
I'm wondering, so you mentioned the paper of Sahani about unified framework where she looked at different methods, right?
Yeah.
So can you also place your method in that framework, or is it
it's basically a direct continuation. So they also make this ansatz with.
Yeah, they also have this A and K, right?
Yeah,
and we see a lot of similarities. So I'm just wondering, like, so what is
the difference?
Yeah.
So it's the correlation, taking case of these correlations. We actually just used this because I originally didn't find an EnKF for the correlated noise framework. So basically I knew this method, so I did it mostly by myself. That was the way it appeared in the paper. So it's just their method by Standard, Reif, and Patiraya applied to this correlated noise framework. And what they also don't have is these vectorized form. So they look, so they look at this a little bit different, and yeah, but it's basically just a usage of the method for most part, and usage for the correlated case.
I think we are on time, so we go for a break. For that, please thanks.
那个可能是肖老师的，可能是肖老师的那个，你自己插进去，然后弄一下。肖，我都忘了。
presenting next.
Yeah.
So yeah, maybe it is here. I don't know. Slides. Wednesday. Where is it? Isn't it Wednesday today?
I think yeah, you can just put here.
But okay, I thought it was here.
Yeah, today's Wednesday.
Yeah, okay, yeah.
I saw that you have a study in your presentation. But,
Maybe it's here on the, yeah, there it is. Yeah. So how do I
just
get
make
to
a
the-
copy. Let me do it.
Yeah, okay, yeah.
But default is going to use this what's the name, Edge or something to open it. So we have to open it, use something else. Okay. We want to have a try. Let's see.
Yeah, perfect.
Okay, that's good. Yes.
Yeah, put it back in full screen.
Yeah.
I'll check if the pointer works.
Yeah. That pointer doesn't work. Does not
Okay.
work. Yeah.
Where is the other one?
Yeah, that one is.
You perform zero simulations using this computer, or it's a single?
But I think I have to wait for Guanglan to upload this presentation.
Oh yeah, okay.
I will do first. Yeah. Then you both can have a try.
下一个是 Charles。
那个我看一下，这个是你的是吗？
啊，对。
OK。I made a wrong copy. Yeah, you have, okay. That's why I had a vague memory that you did something, but then I suddenly I forgot. But then let's see. So I'll come first, okay, and then Guanglan. So try this. Wait. Yeah, full screen. It works. Okay, very good. Guanglan, do you want to try? I haven't opened your presentation yet. Second is yours. Oh, your is PPT, yes. It doesn't work. Let me see. It's actually, yeah, maybe it's maybe it's actually the lab. No, okay, now it's working. Yeah. Okay, that's good. Yes. Now you are ready. I think you want to use microphone, right? Yeah.
So something I rang it incorrectly.
Let me mute it right now.
So how is the mute?
Yeah, it's muted. So it's not here. There's a button. You see. Now it's
there,
muted,
okay.
and
Yeah.
The other way is.
So how do you do this?
View. You go to view. Then you will have this. There is no view. Yes, this one.
Full
screen mode. Yes. But it's only after you start to share your screen. Then you go to the
okay.
full screen.
So I share screen and then put it in full screen.
Yeah, exactly. I can come up to help you.
Yeah.
yes, made by this. This is the purpose for the collection. In fact, inflation factors. They apply the they apply Emily proved that when you use the inflation factors, the results is the same when your knowledge is one. So because this I have this splash, I don't know if it's not curiosity. I think this might be this provide the same result.
Yeah, actually, I put that in. Yes, I started doing PhD.
I don't compare with this. You can assimilate all options from your network to my options. Here you are
some problem. For example,
depending of the solution of the
it's not possible to mix with some kind
may induce some overfitting. If you don't use this solution, so I must have come this. If you need some control like alpha here to avoid this overfitting.
Maybe narrow down gradually.
If you apply the SMBA, but without using the
So like not like
in his paper, shows that the alpha for the linear motion provide the same results. For the alpha, there's one continuous respect. Using alpha,
only
it's a little bit.
Before that, you can check if that's happening from
So we don't know where when they are going to be raised up. So maybe like after one, so more you can say, okay, let's do like a horror.
There are some sneakers that create the value now with the object function. So the alpha over the iteration is slightly higher. So you can calculate that to know how of beta instead of 3%, then what is the here I apply adaptive. And he follows Alpha is like oh my God, you know, you should have said that.
Paul, almost your time.
So it's 4.
Okay, everyone, let's settle down for the next session. So, get the share screen first. Oh, view. And then that's good. Yeah. So, everything works. So, our next speaker is Håkon. Talk about sparse matrix formula of model-based ensemble. Yeah. Thank you for the introduction. Can you hear me? Yeah, good. So my presentation is entitled a sparse matrix formulation of the model-based ensemble Kalman filter. So I changed the title a little bit, and this is joint work with my supervisor, Håkon Kjellberg. So here's the outline for my presentation. I'll first talk about the standard EnKF, in particular the update step. And then I'll talk about some of the issues with this standard EnKF or the update step. And as a result of this, I will talk about the model-based EnKF, which is addressing these problems and which was introduced in a paper from 2020. But this model-based EnKF has some problems with computational demands. So therefore, I will talk about those problems and present a new strategy where I solve these problems. And lastly, some results and some closing remarks. So I have this state space model here. So I have a forward model G, which can either be linear or nonlinear. And I have an observation model, which is Gauss linear. And my aim is to assess the filtering distribution. So first, I'll talk about this update step. So you are probably familiar with this update step, but I want to explain it how I view it as a statistician. So we assume that the forecast ensemble members are IID realizations from this distribution here, and that mu and sigma are unknown variables. And then we use the forecast ensemble to estimate these parameters. And this model here, or this figure, shows the same. So this square here indicates that the forecast ensemble members are something that we have observed. And this circle indicates that mu and sigma are unknown variables. And the second part of the update step is to update the ensemble members. So when we update ensemble member number m, we assume the following. We assume that the forecast ensemble member comes from the same distribution as the true underlying state vector, given our model parameter estimates that we found on the previous slide. And recall that we have this Gauss linear observation model, which you see here. And then when we update this ensemble member, we require the following. The ensemble member, which has been updated, so the filter ensemble member, should come from the same distribution as this state vector here, given our model parameter estimates and our observations. That is our requirement. So this D here means that they are equal in distribution. And then it can be shown that this standard EnKF updates satisfies this requirement. And it can be shown also that this square root filter satisfies the same requirement. And I will talk more about this square root filter later. Yeah, so this is in short how we do this EnKF. So the problems with the standard EnKF are the following, or some of them at least. The uncertainty in the estimates is ignored. We don't know if our estimates are good or bad. Yeah. The second problem is that the information in the forecast ensemble is used twice. First when we estimate mu and sigma, and then later when we update the ensemble members. And number three, the information and the observations about the model parameters is ignored. And number four, why are we using this standard EnKF updates? We could have used the square filter or some other filter, but for some reason we are using this square filter. No, sorry, this EnKF update. And lastly, the EnKF has a tendency to underestimate the uncertainty, as you probably all know. So as a result of this model-based EnKF was introduced in 2020 in a paper by Margrethe Kallevold and Håkon Kjelland. So this model here combines these two existing models that we use in the standard EnKF. Yeah, and Håkon Kjelland actually introduced this model or presented it at the EnKF workshop last year. Yeah. So in the following, I want to discuss how this model, how it is used in practice. So we still assume that the forecast ensemble members are IID realizations from this distribution, given the model parameters. But what's different now is that we now assume that mu and sigma are stochastic variables. So now we assume that they come from a distribution, namely the normal inverse distribution. And we still assume this Gauss linear observation model. So when we update the ensemble member number n, we require the following now. So this is a different requirement from the previous. We require that the updated ensemble member should come from the same distribution as this ensemble. No, sorry, not from this as this state vector. Given all of the forecast ensemble members except the one that we are updating. And we also condition on the observations, which you see up here. And instead of using this standard EnKF updates, we want to find an updating procedure which is minimizing this optimality criterion that we see down here. And this results in the following algorithm. So we first sample mu and sigma from a distribution, namely a normal inversely sharp distribution. And this distribution is conditioned on the forecast ensemble members, except the one that we are updating, also the observations. So notice here that we are sampling mu and sigma and not estimating. And then we compute this Kalman gain and some weight matrix B, and we do the following updates. So this update procedure here is a particular type of square root filter, and it's the updating procedure that we found to be optimal according to our optimality criteria. And the paper that introduces this model-based EnKF shows that the results are promising and that the uncertainty representation is realistic. But however, there is one problem, and that's the fact that this model-based EnKF is very computationally demanding. So in the following, I want to discuss further why it is computationally demanding and what we can do to solve it. So the first problem is sampling from this distribution here, the normal inverse V-charge distribution. And the problem here is that sampling from this distribution is computationally demanding. And that has to do with the fact that in order to sample from this distribution, you have to do Cholesky decompositions of a full matrix. And the second problem here is that sigma is a full matrix. So what we do here is the following. You see, is it working? There, yeah. So we use precision matrices instead of covariance matrices. So a precision matrix is the inverse of a covariance matrix, and we choose a distribution for this precision matrix such that we can sample it efficiently and such that it becomes sparse. And we can achieve this by imposing a Markov property on the state vector, such that we get a Gaussian Markov random field. The second problem is regarding this updating procedure here, which we found to be the optimal updating procedure. So in the following, I will call this the optimal updates. So if I'm referring to the optimal update later, it's this equation that I'm referring to. And the problem here is computing this B matrix. So this is, in short, how we compute this weight matrix B. And what you need to know here is that the first 3 steps can be done efficiently. And that's because this Q matrix is a sparse matrix, or in particular, a band matrix. Step number 4 is not computationally efficient. That has to do with the fact that singular value decomposition is not efficient for high-dimensional matrices. So even if this matrix C here is sparse, we cannot do this efficiently. So here we have to come up with some approximation to these optimal updates. So what we do is the following. We take the state vector and we split it into multiple blocks. And then we update each of these blocks individually. So let's assume that the state vector can be structured into a 2-dimensional grid, as you see here, and that we partition all of these elements into multiple blocks. And then we want to update each of these blocks individually. So this here resembles domain localization, but our motivation is different. So the reason why we do domain localization in general is because we want to avoid spurious correlations. But here we do these block updates to reduce the computational demands. So let's say if you want to update this block here, this CD block, how is this done in practice? First, we define a block DB and a block EB. And then we take all of these elements here in red, they're supposed to be in red, yeah. And we set them equal to their own mean value. And this is an approximation, but it's a reasonable approximation because we can assume that these elements here, they are more or less independent of the elements inside this CD block. Then we take all of the elements in yellow. Yeah, I think you can see the colors, but it's the elements that is inside this area here. And we marginalize them out of this distribution. And then we compute the optimal updates for all of the elements in green, but we only use these updates to update the elements in blue in the middle there. So this is, in short, how we do this block updates. So this is then an approximation to these optimal updates. And now we want to see how well this performs in comparison to this optimal update. So what we do is the following. We want to compare the optimal update and the block updates in regards to the computational demands and the results. So first we want to look at the computational demands because the block update is supposed to be a fast alternative. So if it's no faster than the optimal updates, then there is no reason why we should use it because it's an approximation. And then secondly, not only do we want the block update to be faster, we also want the results to be of similar quality as the results that we get with this optimal update. Yeah, So we consider the following simulation example. So we assume that this state vector is constructed on a quadratic grid of size s times s, which is two-dimensional. And then we assume that x1, so the initial reference solution, is some Gaussian field with some spatial correlation structure. So you see one realization of x1 down here. And then we have a forward function, which is deterministic and which is smoothing around the center node. So here you see that when time evolves, the reference solution becomes smoother. And then we choose a vague-prior for mu and q, which is set to be the same for all the time steps. And our observations, which you can see here, they are computed using or simulated using a local average with some additive Gaussian noise. So now we will first want to compare the two updating procedures, the optimal and the block. And we first want to look at the computational demands. So here I run both of the methods on increasing grid sizes and looked at how the CPU time increases when the dimension increases. And I also
just the first one. When you say the observations are local averages, is that what you said?
Yeah, yeah.
Is it like over a spatial average?
Yes.
Like how much?
I don't remember the exact number, but yeah.
Okay.
Yeah. But here you have the reference, and here you have observations. So there's some similarity. Okay. Yeah. So here I computed the CPU time when the dimension increases. And you see that for this optimal updates, the CPU time increases very rapidly when the dimension increases. But for these block updates, the steepness is not as large. So the CPU time is lower when the dimension increases. So this is promising. And now we want to compare the results. So we run both the block updates and the optimal updates on a grid of this dimension. And then in the block update, we use blocks of size 20 times 20. And these two ensembles that we update, they are updated using the same forecast ensemble observations and model parameters. So if these two ensembles that we get are different, it's because the updating procedures are different, because everything else is similar. So here you see the ensemble average with the optimal updates at iteration number 3, and the same for the block updates. So they look kind of similar, but it's hard to tell how similar they are by just looking at them. So if we look at this cross-section of this grid and compare it to the same cross-section of this grid, we get this. So here you see the reference solution is the black line, and the observations are the red dots, and the two ensembles are the yellow and blue curves. And yeah, it's hard to see the yellow curve, but it's pretty much overlapping with the black. So the middle curve here is the ensemble average, and the lower and upper curve is the empirical bounds of the prediction interval. So here we see that they are pretty much identical. You can see there's a small difference here if you look very closely, so they're not entirely identical. And then we can also look at the ensemble averages and then look at the difference between these two. So what we just looked at was this cross section here. And so here's the difference in the averages, as I said. And you see that the error is quite small inside these areas here, but along these lines, the error is bigger. And that's because in this block update, I use blocks of size 20 times 20. So you see along the borders of the blocks, the error is larger. And here you also see the same for iteration number 1 and iteration number 5. Yeah. And then in this next example, I have computed the optimal updates and the block updates on a grid of size 100 times 100. So this is one cross section. And here we see that the ensembles are similar, but they're not identical. So they're not. So they are similar because the observations that are used in both of these examples are the same. So they're conditioned on the same data. But they're not completely identical. That's because first, the updating procedures are different. So there's a chance that there's an approximation error here in this block update. but also the ensembles themselves are different. As you all know, when you do ensemble gamma filter, you sample the ensemble from an initial distribution, and therefore you never get the exact same solution every time you do EnKF. So there's also a chance that these two plots are different because the ensembles themselves are different. So
sorry, what is this? Isn't this just a matter of setting the seed?
yeah, we could have, but actually what we did here. But yeah, I'll get to my point. Yeah. So we want to now look at, is this approximation error here large compared to the overall variability in the EnKF? So if you run both of these methods one more time, we get this. So you see that these two ensembles, they are different, even though the updating procedure is the same, meaning that the variability in the EnKF is quite large compared to the overall approximation error here in the block updates. Because you see that there's reason to believe that the difference between these two plots is no larger than the error between, or the difference between these two. And in this last example, I want to look at how the block update performs on a high-dimensional grid. Because the problem with this optimal update is that we cannot run it on high-dimensional grids because it's so inefficient. So that's also one of our motivations for introducing these block updates. So we compute this block updates on this grid size, and we run it for 10 iterations. And here you can see the ensemble average at iteration number 9. So if we again look at this cross-section of the grid, we get this. So again, the black line is the reference solution, and the ensemble members are the green lines. So we see that the ensemble is able to follow the reference solution quite nicely. So it's reasonable to believe that the block update also works well on a high-dimensional grid.
Can I just make sure I understand what you're showing here?
Yeah.
Those red dots.
And that's the iterations.
Yeah, but are they spatial averages?
Yeah. So they're, yeah. But I think yeah. And you can also see that there's some, the variance in the reference solution is also not constant here. Yeah. Yeah, so to sum up, we formulate a new strategy where we use position matrices instead of covariance matrices. And these position matrices are sampled in such a way that they are sparse. And then we introduce this block update as a fast alternative to this optimal update. And the results shows that the block update is faster than the optimal, and that the results are of similar quality. Yeah. So yeah, thank you for listening.
Plenty of time for questions.
Okay, I only have one question. Thank you for the nice talk. My question is, will you not run into the same problem that EnKF's hierarchical filter had, that if you're sampling the hyperparameters, covariance, you get terrible sampling error in the sampling error in them, which is large, will also impact your ensemble hyperparameters?
I'm not sure if because this sampling from this sampling is mu and sigma, that's another yellow pending also. Yeah. That's where it originally came from. But what's the sampling? You think here? Yeah.
That will impact your optimal fit of the numbers themselves.
Yeah, maybe. I don't think. Yeah. I don't talk about that.
I think that was the bane of the pending on that filter.
And no, the problem with this filter was that sampling from this distribution here is very inefficient. So it's infeasible for I don't think it's yeah, I haven't looked at that, but yeah. Yeah, we can discuss that further afterwards. Yeah.
Yeah, so this is very nice. Thank you for that presentation. But as Patrick mentioned, I mean, basically it's optional because it's also time demanding to sample problems. But then
Mark UK just integrated it out instead. So then you take into account the whole uncertainty and you get one cost function, and then you can do the subspace EnKF, and then you have something similar. So I would like to see it, because now you're comparing your block aspect with your optimal, but that's fine.
Yeah.
But it would be very interesting, the optimal versus the integrated out version from Mark. But then, and there is no sampling error, and
Yeah.
it should be.
I'm sure about that, but yeah, we should discuss it further. Thank you.
You've got somebody online who understands.
Laurent, do you have a
No,
follow?
who's the question was over?
Okay.
Oh, okay.
I don't see any.
No, okay.
Yeah.
Laurent said.
Yeah, actually, I have raised my hand. I don't know if you are looking at Zoom.
Okay, let me stop sharing first. Go ahead, Vikram.
Yeah, I thought the protocol is to raise the hand on Zoom, so that's what I did. So my question is, early on in the slides, I think slide number 3 or 4, you said that EnKF ignores the uncertainty in mean and covariance. So are you referring to the uncertainty due to the small sample size or due to higher moments if the problem is nonlinear?
The question is it because we have too few ensemble members, or because, yeah, I don't
Of the non-Gaussian in a non-Gaussian problem, mean and covariance will have non-zero higher moments. So that statement you made was about uncertainty due to small ensemble size or due to non-Gaussianality. I think slide number 3 or 4, very early on, you say that.
Well, when we don't have a prior on mu and sigma, then it's impossible to account for the uncertainty. That's the problem. That's why we're using this prior distribution, because then we can account for this uncertainty.
Okay, thanks.
Francesco?
Oh, sorry.
Thank you for the talk. It was very nice to see macro properties and the precision matrix in the ensemble column filter. I think that's the future of the ensemble column filter.
Yes.
But I was, so we discussed this earlier, but you had a slide or something saying that you use the ensemble members twice.
Yeah.
And in the ordinary formulation of the ensemble converter, which is slightly different from yours, but I struggle to see there how you use the ensemble members twice, at least in the standard formulation. You use them once to estimate the mean and variance matrix, and then you have a influence adjustment leading to the n-1. But is it that your formulation is different and that's why you use ensemble members twice, or are you saying that this is the case also in the standard ensemble converter?
So we first use the ensemble members here when we sample or approximate, when we approximate mu sigma, and then later when we do this update here. So here we use it the second time. That's what I meant by using it twice.
Is it problematic?
Yeah, well, there are some papers that shows that it's problematic because the variance, I think, is becomes too small when you do this. I don't know, yeah. But when I'm doing this here, yeah, because of this requirement here, we don't use the ensemble members twice. That's why.
Yeah, but if you
are.
No, yeah. Thank you. That's a very simple question. The uncertainty on the matrix and on the mean is removed in the mean field limit, or
What do you mean?
when the number of particles tends to infinity, and so instead of having a empirical distribution, you have a continuous distribution evolving.
Oh, yeah, so if you have enough ensemble members, then you, yeah, okay, yeah, that's probably true, but yeah, so yeah, here's this. But you're not able to yeah, okay.
Yeah, I guess you don't underestimate the uncertainty, but then you're not able to tell if it's large enough. I don't know. Yeah, I think I'll discuss this further. I'm not sure if I understood your question completely.
Okay.
Yeah.
Yeah, so I apologize already because my question, because I'm still a little bit hesitant if I understood one couple of things correctly, and that's something I need. But the system you're looking at here, if I understood correctly, the grid, is that so are you trying to at the moment with this method fit your results to a static situation, or does it, because you had those T5, T3 and iteration steps there, but does the system itself change, or is that just the number of times you iterate through it?
Or you mean examples?
Yeah.
Yeah, the system itself also changes. Let's see. Yeah, here. Yeah.
Getting smoother, right?
Yeah, that's so it evolves over time. Yeah. If that's the answer to your question, or
it raises more questions, but I will not answer.
There's another question online. Yes.
Yes, Anika, you like to unmute? Yes.
I have another question. When you compare with the
I'm not sure we can hear you clearly. Maybe you want to raise your move closer to the microphone.
Is it better like that?
Yes.
Okay. When you compare to the optimal setup, was this also the model-based EnKF, or what was this the traditional EnKF?
It was a model-based. Both of the examples were model-based.
Okay. Have you also compared to the normal EnKF?
The standard EnKF?
Yeah.
No. Well, yeah, but the updating procedures are different. So yeah, that'd be good to do that, of course, but I haven't done that.
Okay, thank you.
But yeah.
Okay, I think it's time. It's a great discussion, and we can still continue in the coffee break. And let's move on to the next talk. And thanks, Anna, do you want to take the microphone, please?
Wait.
Ready? So our next speaker is Guannan Hu from University of Reading. Go ahead.
Thank you. It has been a long day. I hope you are not too tired to listen to my talk, although you might find bothered by the end of it. So in this work, we investigate sampling error in the estimation of observation error covariance matrix using observation minus background and observation minus statistics. So we know that observation error covariance matrices are essential elements in data estimation system, which affect the accuracy of analysis and forecast, in particular when we are simulating observations that contains correlated errors. And here there are generally two kinds of correlated errors that has been implemented in operational applications. The first one is the interchannel error correlation, which has been found in satellite data. And the second one is the spatial error correlation, which is known, we found that in geostationary satellite data and also double radar data. There is a widely used sampling approach, which can be used to estimate correlated observation error statistics. And this is well known as Bayesian diagnostics. In this approach, we use simple statistics that can be directly obtained from data assimilation system. And our goal is to investigate the sampling error of this method. So the first statistic we need to use is the observation minus background O minus B statistics. So which is basically taking the difference between observation and the background in observation space. We can also call it innovation vector, it's the same thing. And then for the second line of this equation, we add a term T, which is the truth in observation space, and then we subtract it. So, and then in the item in the first bracket is the observation error. And for the second one, we consider linearized observation operator, and we have this one. And XB minus XP is the background error. So in this way, we reformulate the innovation vector as the difference between observation error and the background error in observation space. And if we take the statistical expectation for this O minus B statistics, we just substitute the equation in here, and then we expand this expectation. Then we have four terms. And in here, in the second line of it, the second term and the third term are zero because observation error and background error are usually assumed to be mutually uncorrelated. And then we find the third line of the equation. And the first expectation gives us the matrix R, and the second expectation gives us the matrix B. And we call this R plus HBH transpose the innovation covariance matrix. And the second statistics we want to use is the observation minus analysis statistics, is O minus A. And similarly, we just take the difference between observation and analysis in observation space. And we consider a simple update for analysis with we call blue, which is the best linear unbiased estimator. So it's given by adding a perturbation of small quantity to the background that we get analysis. And here, this small perturbation is given by the product of common gain matrix and O minus B statistics or innovation vector. And here, the third line of this equation, what we want to do is to expand this term into a Taylor series. So we just have a linear H, and here is the arrow on the second order. And then if we omit this arrow term, we get this one. And this one can be finally reformulated in this one. So we have a relation between O minus A and O minus B statistics. Now I just want to remind you what we have so far. The first is expectation of O minus B statistics, and the second is the relation between O minus A and O minus B. So what if we take the expectation of the outer product of O minus A and O minus B statistics? We can find we can obtain the matrix R. But this is a big note here, is that in this case, we'll assume that the error covariance matrices used in data synthesis system describe the truth completely accurately. Otherwise, we don't have this equation. Otherwise, this expectation gives us an estimated R, which not necessarily equal to the true R. And some remark on this diagnostics. The first is, this is a commonly used technique to estimate correlated R. And the matrices estimated are usually noisy and have to be reconditioned for operational use. So what is sample covariance matrix? We have the equation, the innovation covariance matrix can be obtained by this expectation. And then in reality, we want to use a finite number of samples to estimate this expectation. So here N is the sample size, and this is the X sample, and overlapping knows the average, the sample average. And for the matrix R, we have such a formula, and then again we take the sample parameter of R as this way. We're using N sample size to estimate the expectation here. And there are some previous work on sampling error, which are given by Lidort and Wolf 2004. And they define expected product loss of sample covariance matrix as this way. They take the difference between the hat, which is sample matrix, and B is the true matrix, using the Frobenius law, which is just the element difference between two matrices.
As for clarification, I thought usually when these diagnostics are employed for covariance estimation, that the expectation is approximated with a sample average that is averaging over time, not over the numbers.
Yeah, you're right. I just take samples over time. The samples.
Okay.
Yeah, you're right. And so I will talk about these 4 factors. But yeah, they show that this expected product loss can be reformulated into 4 factors. And I will introduce all of these factors one by one. And the first factor is just the ratio of the number of observations and sample size. So here M is the number of observations, is the size of the matrix, and N is the sample size. And the second factor is the mu square, which is the square of the average size of the diagonal elements. So the trace is just defined to the sum of these diagonal elements of D. And before I introducing the third factor, I would like to give some background. Considering we have eigenvalue decomposition, here D is the matrix whose columns are the eigenvectors of D, and lambda denotes for the eigenvalue. And then here is we have n sample, n of n observation errors. And then what we want to do here is we project correlated observation errors onto the basis given by U transpose. In that way, we obtain a set of uncorrelated observation errors. You can consider that tau is such a matrix. And then the third factor is defined as the variation, is somehow described the variation in the mean size of the square observation error between samples. So it gives us some information about the variability between samples. And here, this is just the first column of tau. I'll take the variance of this. And the Lidor and Wolf, they showed that this factor theta is bounded as goes to infinity. The last factor is the sum of the squares of the eigenvalues divided by n and n. And another good thing is that they also show that beta converges to 0 as n goes to infinity. And our contribution to index summing out. First way define, we like W equal to this equation. And then we find that R equal to W times B. And then a hat equals to W times the hat. Then we can write the expectation quadratic laws of our index sampling of a hat in this way. And here what we want to do is we want to take this W outside of this expectation or outside of this probing now. And we find this equation satisfies such an inequality. And here S denotes the square, S denotes the largest singular value of W. And W is not necessarily symmetric. In many cases, they are, but they are not, it's not necessary.
Can I ask another clarification?
Sure.
Did we make any for the first expected value of D, or D minus D?
Yeah.
Did you make, what were the assumptions on D? Was it the innovation matrix covariance, or was it a general covariance of with some
Innovation, the innovation covariance.
Was it?
Yeah. We check, yeah. And yeah, and now compared to the dark sampling error, for the indirect sampling case, we have a filter factor, which is the largest singular value of W. So if W is symmetric, then this equals to the eigenvalue, the single value, and eigenvalues are identity. And we perform some numerical experiments to demonstrate some result. And we consider equally spaced model grid points on a latitude circle on the earth or any circle. And we consider our observations are taken alternatively. and we use the coexistence. And for the error covariance modeling for the B matrix, we use the SO correlation function, which is the second order autoregression correlation function. And for the matrix R, we use the first order autoregression correlation function. And here sigma B and sigma O are background and observation errors and deviations, and O and B are background and observation error correlation line scales. The reason we use these two correlation functions is that they have been used in operational applications to model B and R. And this is plot for the for and so correlation matrices. And if we have the same error correlation line scale, we can see that so has a heavier tail. That means the correlation drops lower to 0 compared to the 4. And for a single correlation matrix, if we have a larger correlation line scale, we can expect a heavier tail. This is the middle row of the matrix. And then we want to see how the sampling error changes as sigma O, the observation error standard deviation changes. So we can first look at this black line, which is the sampling error. That means sampling error increases as sigma O increases, and all the other factors do. And then we show the sampling error as a function of background error standard deviation. In this case, we note that the sampling error doesn't increase as sigma B increases. This is merely because there's two factors. The first one is the mu square, which increases as sigma B increases. But this singular value S1, it decreases as sigma B decreases. And the other two factors, we should say that they are quite smaller quantities compared to the first two factors. And yeah. And we also want to show that how sampling error changes with observation and background error correlation and skills. Because error standard deviation and error correlation and skills are some basic error statistics for when we model B and R. And here we see beta and theta are again very small quantities compared to S. And that means the index of error is mainly determined by this S. And if we compare this plot with previous plot, we can see that O and LB have smaller influence on the sampling error than sigma O. By the end of this talk, I want to show you some results for sample eigenvalues. Sample eigenvalues are the eigenvalues from the sample covariance matrix. I want first to define such the spread of the sample eigenvalues around the mean of the two eigenvalues. Here, mu R is the mean eigenvalues, the mean two eigenvalues. And then the variance of the two eigenvalues are computed as this way. And they have shown that as the sampling error decreases, delta converges to delta reference. So this has been shown in this plot. Plot A is that we are varying sigma O while keep the other parameters constant, and then plot B is we vary sigma B, and plot C is we vary LO, and plot D is we vary LB. We can focus on this plot. In this case, if alpha increase, that means for a given number of observations, we are using smaller and smaller sample sets. So that means if alpha is larger, than we have a larger difference between delta and delta reference. And some information we can obtain from this plot is that if we have a larger sigma O, then we can see the delta converge to delta reference slower. They need more sample sets to get a good result, to get it to come close. And yeah, this is consistent with the previous result for sampling errors. And some next results shown here, but unfortunately, this is for this stage, this is just a result from numerical experiments. We are trying to find some theoretical basis to back up this. And in this plot, we see that the sample eigenvalues, the largest sample eigenvalues are larger than the true largest eigenvalues. While the smallest eigenvalues, the smallest sample eigenvalues are smaller than the true eigenvalues. Why this is important? For example, in variational data assimilation, studies have found that the smallest eigenvalue was found to affect the speed of the convergence of the minimization in variational data assimilation. So we want our estimated eigenvalues as accurate as we can, so that we can, And a summary for this talk. The first point is that the sampling error is mainly affected by observation error standard deviation compared to the other error characteristics. Of course, the largest factor that changes the sample error is the sample size. And the numerical results show that the largest sample eigenvalues are greater than the true values, and the smallest sample eigenvalues are smaller than the true values. And we hope that our results can provide some guidance in deciding on appropriate sample sizes and choosing parameters for matrix reconditioning techniques. Yeah, and these are some key reference. Thank you.
For now, we have 12 minutes. Oh, that's awesome.
So 2 questions for both are quick. The first is that this is more that, have I understood it correctly? Now that you've done it. So I've always understood that within the field, it's the observation uncertainty, error covariances have accepted the error factor and like that, but in actual systems that they are really difficult to actually, much more difficult naturally than determine than the flawed background error covariances that we get. Is this the right understanding?
Yeah, in this way, we just estimate the R matrix for the observation covariance. We didn't want to estimate the background.
No, but I was asking that, is the main reason from your perception why the observation, this isn't like, this is just check it, and if I've understood correctly, it has been that the difficulty of estimating that observation covariances. Has that been the main reason why they haven't been applied so much so far?
The reason, I don't think so. This is really, they have been applied so far, the correlated errors. They have been applied in some cases, but it really depends on which type of observation you are looking at. There are many type of observations, they don't have correlated errors. At least we didn't find it, that they are correlated. But for some time observations for geostationary satellite data, it's not the satellite, the satellite in general, just the geostationary satellite, it's not orbit satellites. They have been shown to exhibit some spatial error correlation and also Doppler radar data. But if you don't implement them, you can still have some good results. But after you implement the correlated errors, you'll find the result even better, because as the previous studies have been shown.
Okay, you actually indirectly answered my second question, so I can already.
Oh yeah.
Thank you.
Patrick.
Just wondering, some general question that maybe I could talk to here, I'm not sure, but I noticed in observation error covariance estimation, not the statistic usually used is observation minus background times observation minus analysis.
Yeah.
I wonder why not the other statistics, the one observation minus background squared, if you will.
Yeah.
And then minus just the prior.
The prior would mean required in the background.
Yes. So that you will have, HPH plus 1, that will be the expected value of the first, and then minus HPH is the second. There are 2 ways of estimating from there was 2 ways of estimating the R matrix. one is the one you use, and one is the one I'm mentioning now, and I'm curious why the one you use tends to be the one most.
I need to think what you, because I didn't follow the equations you just mentioned. But we can talk, might be, but this method, because in the previous book, they have used this almost and
Well, I can jump in on this a little bit. Maybe I can talk. So when you have uncertainties in a different part of the innovation, these two different formula has relatively different accuracy. My impression is that. So sometimes, because you can think about that triangle, right? This is O truth and B, and if you have this wrong assumption, one leg is too short, and that innovation statistics can break down in one of the geometry relationship. Right? I've tried that many years ago, but I forgot. So, any other questions?
A quick one. So
wait for the microphone. Oh, sorry. A microphone for. Sorry.
Embarrassing not to wait so long for a simple question. No, so even once you get R, I mean full R, then is it being used? Is it possible to use it in let's say a global weather system, or is it, do you use small R's because you're using local analysis, or how does it actually work in practice once you've computed one?
Yeah, this is a really good question, because of course if we use a full R, then the computational cost is very large. For example, we cannot do the inverse of R. In the variational system, we need to invert R. And the method they use is to take the terrestrial computation, someone has mentioned that before. And indeed, this R is not being used globally. For example, there's a study conducted by David Simon. They have implemented the correlated R in W. So they use the terrestrial decomposition to follow the inversion of R. You need to use some numerical approximation method to achieve that.
It's Igor talking. So I just want to link to my knowledge from previous studies. So like, are you aware? So some people use still diagnostic, diagonal matrix, but inflate the current observation error variance by some factors. Do you think it's can be explained by your result or some summary? Which the observation error variance is important in the sample error part.
Yeah, I was trying to think this, so maybe can you repeat that? I didn't really pay attention. Sorry. So can you repeat your question?
So what it means? So in your, if you go to your summary slide, So I think okay, correct. So the sampling error is more affected by observation error. Variance or standard deviation. So when I saw some study, previous study, they just use your R matrix, diagnostic matrix, and they inflate. And always there is correlated error. But they inflate the diagnostic.
You're right. There are many ways. Like Western, they have shown that if you want to account for correlated of the errors, you can actually inflate it. Just inflate the diagonal matrix. You can. But now we are trying to make it but in this way you didn't use the information. You didn't use the information for our correlation. We are trying to really explicitly use the information from our correlation. So we are trying to use a full matrix. So result have been shown that this can beat the just inflation for some time. That's some cases. I ask another question.
Sure.
So here you so from this formula you use analysis or background both. I mean, and you or sampling from time from 1 to until. So that's meaning you do once whatever EnKF or data estimation, and then you estimate the R. Yeah. Then you perform once more. Yeah. And then you get new analysis, right? What I mean is it's not.
This is time evolving.
Yeah. Yeah. Time evolving also. So I mean, you can ask a new R. Yeah. It's repeat. It's iterative. Iterative. Sorry.
Over and over again. Yeah, that means in reality, we really use a huge amount of data. That means we take the O minus A and O minus B for different time steps for really long time steps. So that means we may have a kind of convergence for estimation. So that means why in many cases they didn't really care about standard error, because standard error is larger only when we don't have enough sample.
Thank you for the presentation, first of all. I have a double question. First regards the nice structure, the smooth structure of this correlation metrics. All the times I see such a result, I ask myself, does it mean there is some underlying physics that's regulating this correlation? Yeah. The second question regards time dependence. Like all this is done assuming that there is correlation in space and no correlation in time. Something changed if we assume there can be correlation in time.
Yeah. So for the first question, I think the only physics here is that we assume that the error correlation, the spatial error correlation decays as the distance increases. So that means we have a smoothing function. And for the second question, we didn't consider any correlation in time, but it's a good question. Maybe in the later, in some time point, people will trying to also implement observation correlation in time for operational applications. But to my knowledge, they haven't been applied yet. Of course, if we consider our correlation, they may different correlation function.
Okay, thank you very much. I think it's time for another break. I see a lot of tired faces. Yes, thanks, Guan Ange. I'll come back in 15 minutes.
那个 Andreas， 那你不用管了，那个我来看。Hi, Matthew, are you there?
Hey, yeah.
Hey, nice to see you.
Good to see you too.
Yeah, we like to try and to share your presentation to see if the sound and video works. Sure. Because we got some problems, so it's better to try that out first.
Sure. Should I share my screen?
Yes, yes, please.
Do you see this?
Yes, I think it works. It's very good.
Great. Great.
And you have 45 minutes, yes.
45 minutes?
Good. Yeah, I think I see that you only have 30 slides, so take your time.
Okay, great, thanks.
And reserve 5 minutes for questions.
Yeah, I figured I would leave plenty of time for questions.
Okay, that's very good. Yes. And I think you can just leave your slides there, because when you start, then we can save a little bit of time for you.
Okay, perfect, thanks.
Okay, thank you.
Okay, I think we are basically everyone is here. So let's start the last session of the day. It's been a long day. Rolf, can you lock the doors so nobody can leave? So our first talk today is machine learning of model error in dynamical systems from Matthew Levine at Caltech. So please, Matthew, the floor is yours.
Wow, great. Thank you so much. So I really appreciate the invitation to talk to you guys today. And I know I'm on US time, so I'm just waking up, but hopefully you guys are also still awake. So yeah, thank you to Xiaodong and Gear for the invitation. So what I'm going to tell you about today is machine learning of model error in dynamical systems. So I'm a fourth year PhD student with Andrew Stewart at Caltech. And so this is the work that we've been doing together through my PhD. So let's get started. So I give this introduction and it's always, I feel, preaching to the choir. Lots of folks like machine learning and it works, in fact, when you have enough data. And mechanistic models are also wonderful. If you know how physics work and you have enough knowledge and enough ability to compute, then those are awesome and you can predict all kinds of things based on physical models. And I would say at this point, I feel that a lot of open prediction problems are settings where we have some data and some prior knowledge. And so I feel that the next generation of high-performing prediction models are going to hybridize both physics-based and data-driven modeling techniques. And so the question I tried to ask myself at the beginning of the PhD was, how can we help to lay the groundwork for this future? So the setting that I'm going to consider is where you have a ODE that we think of as a true system. So it's some variables X coupled to variables Y through an ODE, and perhaps there's some scale separation epsilon between the dynamics in X and Y. Although this scale separation, you could think of epsilon as being 1 and this just being a large coupled system. And I think this is super relevant across disciplines. Many of you in the climate and weather communities and oceanography communities think about systems like this, but it's also relevant in physiology and biology and celestial mechanics and all kinds of places we see ODEs. And so my goal for studying the system is very simple. It's to say that if we are given noisy observations of the X component, in other words, like a subsystem of this equation, can we learn a predictive model for future dynamics of that partial observation? And the constraint is that I may only have access to partial noisy observations of this true system. I observe X, but not Y, for example. And furthermore, because I'm observing X, I have no knowledge of Y. And in fact, in many cases, I may not know anything about the governing equations for the dynamics in Y. In fact, I might not even know the dimensionality of this system in Y because it's something I didn't measure and maybe didn't even know was there that was forcing the thing that I'm observing, which is X. And furthermore, we may observe this system irregularly spaced and noisy. So you don't necessarily know how your observations are going to come in. And finally, I also want to be able to predict the system using all the knowledge that I already have. So if I write down the system, a lot of times we may actually have some partial, pretty good knowledge of how FDagger works, perhaps on just the space of X. So maybe I'll give a little bit more insight into that. So how can we leverage partial knowledge of the dynamics? Well, a really simple way to write this is to just rewrite that previous system of equations using an F0. So I'm going to call F0 kind of my nominal physical model or mechanistic model that I have or a practitioner has. And for any choice of this model, there exists a correction function, MDagger, such that I can rewrite the previous equation in this form. And this shouldn't be mind-blowing to you. I mean, if I pick F0 to be 0, then MDagger is just FDagger from before. But you might hope that, in fact, F0 is pretty good. And so suddenly these residual dynamics, which I'm calling MDAGR, get smaller. And then perhaps they're going to be easy to cope with or learn, right? And so this is the motivation for kind of starting with what you know and then trying to infer what you don't. And in fact, we can write this whole system just in terms of X. So there's actually a memory dependent closure, you might say, that captures the entire effect of the Y system on X by just keeping track of the whole history and the initial condition for Y0. So we would call this closure term having memory. But I mean, you guys probably have seen this a ton with closure modeling, that of course, when epsilon goes to 0, in other words, your Y dynamics start moving very fast relative to X. So then we might expect that there's actually a closure that only depends on the current X. So in other words, I don't need to keep track of history. Y is moving so fast relative to X that I just can look up an average value of Y, and that's enough. And so this is kind of relates to results in homogenization. But the point here is that you might be able to hope that the original system can be reduced to something in this equation 4, where now we just have a lower dimensional object just on our observations X. And if you observe things, you can actually try to learn this correction function M using any kind of function approximation technique. And maybe you have an idea of where it comes from and you can design something that fits well. But that's a general idea. But if we just step back, what is kind of the big picture? So I try to give like a toy example. I mean, many of you are experts in multi-scale modeling and I'm not. But so let's picture a multi-scale linear oscillator. So let's just first start with a simple 2-dimensional linear oscillator, which is x dot equals ax. I don't know if you guys can see my cursor here. Oh yeah, there we go. X dot equals ax. Okay, and A is a rotation matrix. And so if I were to plot the phase portrait for X in R2, what it does is it traces a circle, right? It's a periodic orbit, this 2D linear oscillator. Okay, so that's great. So that's kind of what we see in the circles. And now what if we created a new variable Y, which does the same thing? It also is just governed by AY. So it's a periodic orbit, but it has a relative velocity to X. So epsilon, when epsilon goes to 0, Y dot gets huge. And so it still spins in the same way as X, but just much faster. Okay. And now what if we were to drive this basic, orbiting system in X by a Y, which is independently oscillating in the same style, but just faster, right? And what we see here is I'm plotting the phase portrait for X1 and X2 across different values of epsilon and coupling. And so what we see is as epsilon goes to 0, which is at the top row, we get this averaging effect where Y is moving so fast that it averages out, in this case to 0, but the point is it averages out. And as Y slows down relative to X, you get this kind of like spirographic picture, right? And so I would say that the situations on kind of the top left are relevant are kind of memory lists, and you would get away with modeling just in terms of the X variables. And you could do a Markovian closure, we might say. On the other hand, on the bottom half, say this lower triangle, this is where memory becomes present. If you want to keep track of even the average statistics of this system, they're not given by an ODE on X, right? This flower picture cannot be described with a 2D ODE on X because the paths cross, right? So this is kind of the picture to have in mind, and this also relates to some of the more sophisticated models that atmospheric and oceanographic folks might look at. Like there's a toy model, this multi-scale Lorenz 96 model, where it's of the form that I told you about. So you have X dot is some function of f of X, and then it's coupled to some Y. And these Ys are moving chaotically and are driven by X's, in fact. And so what you end up with is a multi-scale system given by Y, and given where the scale separation is a factor epsilon. And so you can apply an averaging hypothesis in this setting to great success and remove this Y variable and just model the system in terms of X. And so this is like a great example of basically closure modeling. And in this case, we tried to learn this closure using a random feature model. So we just learned this residual here, m. And that's what I'll show you is just the picture of the function m as a function of its input. So it has a 1D input because we just we binned across these dimensions k for this system. And so what you can do is just fit this function. You can observe x dot and f and x. Sorry. So if I go back, oh yeah. Well, this is okay. Yeah. Sheldon told me that my slides looked a little short, so I threw a few extra in. So now they might be out of order. But in any case, the point here is that if I try to learn a closure function m, I'm showing that in blue, and I can watch the actual residuals of my nominal physical model fk, and they're plotted in the dots here. And so on average, I'm right, and there's some statistical sense in which I'm not. And if you were to actually look at a trajectory of these residuals with respect to my physical model, you see that the oscillations are tight around this mean that I've learned, right? So this is probably a good setting for doing Markovian closure modeling, because the scale separation is so great that there's a slow moving thing and then a fast moving thing that stays very close to its average. And in fact, you can use this type of model to reproduce various statistics of the systems. You can reproduce its invariant measure. You can reproduce its autocorrelation function. You can learn accurate short-term forecasts by just inferring this closure from data. And I'll just point out here that trying to learn the entire system from scratch, in other words, ignoring the fact that I knew a lot about how the dynamics in X are governed by this FK, if I tried to learn that whole thing, the amount of data that I used to learn the closure function was woefully insufficient. And so I got terrible performance when trying to learn the entire system from scratch. But now what happens if I look at different values of scale separation? So on the left, I'm showing you the same picture from before, where this scale separation factor epsilon is super small. And then we can look at how the residuals with respect to the nominal physical model move as epsilon grows, right? As the scale separation diminishes. And so these might not be as physically descriptive of the particular system, but it illustrates things that can happen, right? So as epsilon gets bigger, we'll see that the variance of the residuals around the mean that I learned get larger. And then the trajectories of these residuals start to take shape. So initially we see this like, stochastic process tight around the mean, but as this thing slows down, you end up with these loops, very slow loops around the mean. And this is kind of that picture I was showing you before with the spirograph. So you may care about systems of this right variety, and it may turn out that Markovian representations of them are just insufficient to describe them. And so how can we try to model things when they're not well represented in the observed variables? Well, somehow we need to deal with this phenomena of memory or missing variables. And the way that I'm going to look at this is in a continuous time setting. So I'm going to say I want to learn some kind of ODE or different system of differential equations that captures the dynamics of my observable X. And generally, I would say that there are two ways to do this. I introduced one of them earlier, which is to recognize that if I have some missing dynamics, I can represent that with delays, right? And in this case, I guess maybe I would say that I'm a little bit afraid of integrating delay differential equations. You can imagine that if you have an adaptive solver and it needs to improve the fidelity at time now, right, xk, if it's a function of this entire history, it has to, potentially go back and improve its solutions at some tau history ago, and the management of this could be quite difficult. But what is nice is it might allow for some good direct supervised training. You can imagine that I just have windows of history predicting observed residual dynamics. The other thing you could try to do is say, well, I started with a model that was x dot and y dot, so maybe I can just try to re-augment the state space. And we can write that by just positing some general functions that we want to learn that might represent those unknown quantities M and G. And so if I have a model like this, if I were able to learn a model of this form that nicely reproduces X, I know how to use it. I can just throw it into you know, an ODE solver and it'll be solved numerically, but the training can actually get quite challenging because if you notice, I'm trying to learn this system where I have no idea what these thetas are. In other words, I don't know the functions M and G, but I also don't know the state of R. R is this like invented concept essentially, right? Which is trying to keep track of missing dynamics that I never observed and don't really understand. And so this can make the training quite challenging. You kind of have a chicken and egg problem of inferring missing states and then trying to infer their dynamics, the functions that govern their dynamics as well. So I think I've talked for 15 minutes so far, so I'm on track, but I wanted to pause because I can't see folks here. I can see Yishuan, but I just wanted to see, are there any questions? Because I do want to make sure that you guys feel comfortable interrupting. Yeah. Are you unmuting?
Can you hear me? Hello? Hello?
Hello? Oh, Gear is there.
Can you hear me now?
I can hear somebody. Yeah, I think I hear Gear.
Oh, okay. It's not Gear, it's Patrick.
Oh, okay. Oh, I see Gear.
Just wondering if you could maybe, because this looks a lot so far to like Wilk's error parameterization paper from 2005. So wondering if you could comment on this comparison.
Which looks like the Wilkes paper? What I've shown you so far is very similar, right? What I've shown you so far is very similar. It's just basically a Markovian closure. So yeah, that's the same. So what I'm gonna try to get to is how to learn latent dynamics that would account for non-Markovian properties, which the Wilkes paper does not deal with, right? So I think it's just fitting like a polynomial to the as a Markovian closure on X, which is basically the same as what I've done here. This is just to set up the problem in some sense.
Yeah, very well. Thank you.
Okay, great, thanks. Yeah, so lots of great methods are out there for what I would call like Markovian closure modeling. I mean, I did one of them, but lots of people are very good at this. What I found interesting is how do you cope with when missing dynamics have an influence that can't be described fundamentally by Markovian closures. And so I'm going to tackle it from this perspective where I try to re-augment the state space. And I'm going to acknowledge that there are many settings where, in fact, you already know this hidden state. Like in settings where there are full physical characterizations of a system, the whole point of closure modeling is to not solve these guys, right, and not resolve them. But I think if we think from a broader perspective, there are many settings where, in fact, we don't know anything about these hidden dynamics. And so it might be worthwhile trying to discover them. And furthermore, I might also argue that even though perhaps, a physical ocean or atmospheric model can write down the equations for this, there might be, I think oftentimes people go from a very discrete jump from write down all the fast scale variables to complete closure. And there may be a sweet spot of having a slower dimensional kind of learnt hidden dynamics that are a little bit more expressive than a purely Markovian closure, but do not force you to resolve every fast scale dynamic that you can write down. Okay, so I'm going to show how you can infer this using data assimilation and machine learning. So first, let me just write down the system again. So on the left, I've written the model, the form of my model, and on the right, I'm just going to rewrite it a little bit. So I'm going to concatenate the right-hand sides to all just be written as F. All of the thetas are just going to be one theta. And so I'm also going to concatenate X and R, the observed state and the hidden state in this variable U, and then introduce some notation that says, okay, I can observe U with this observation operator H that gives me X. And this is just a simplified notation when I write down what we're going to do next. So let's further assume that we get noisy observations, which I'm going to call Z. So basically, these are just noisy observations of X. And let's define a solution operator for our model U. So it's at given an initial condition V and some parameters theta, it integrates this model on the right up to time t, right? Okay. So now what's the first thing you might think to do when trying to fit a model of this form to data Z? Well, you might say, okay, I want to have my solutions in the observed component fit the data, right? And you might want it to fit over a whole trajectory. But of course, in this case, remember that U has to be initialized, and I have no idea what R is, right? So I might be able to, on one hand, I might need to denoise the components of X, but much worse is that I have no idea what R0 is, right? And in fact, R0 is potentially this invented quantity that could have essentially no physical meaning in the way that I'm presenting it here. It's a way to learn something that describes evolution of the observable. And so what some of these folks in the machine learning community did with their like neural ODE business is they said, oh, well, all you got to do is just, fit these things and learn the initial condition as well, right? And of course, I'm talking to the data assimilation community, and you all know the problems with this. If I give you a long trajectory and you want me to learn something from it, this kind of optimization, finding the best model theta and an initial condition to fit a long trajectory is really poorly posed if you have a large T. So if it's a chaotic system, it's going to be very sensitive to the initial condition, and you can't really exploit the data very well. So naively, what might you try to do? You might try to just break the data into chunks, right? Some kind of like 4D VAR style strategy where you say, okay, I'm going to just segment my really long data set into chunks where I can expect reasonable sensitivities, and then fit my model to the observations and try to infer the initial condition of every window. So I just made capital K windows, and then each one has an initial condition U0K now, right? But the problem here is, again, that, remember, we're trying to maybe do this offline or something, but the dimensionality of this inference is still growing with the overall data set, right? The longer the trajectory, the more windows I have to chunk it into, and then I'm inferring more and more of these initial conditions. And so it can scale really poorly. And also, if you use this kind of hard constraint, if you choose too small of windows, you can essentially cherry pick and overfit these initial conditions, right? So you can get an initial condition for each window that happens to fit there, but it's not a consistent underlying representation of the dynamics. And so I think there was a talk from Ronan Fable's group, but so I think one of the nice ideas here is to introduce a weak constraint, which says, okay, I'm going to infer an entire trajectory U of t that has observed components that are close to the data. And then I also want to enforce a constraint, which is that this particular U of t roughly evolves according to the dynamics which I'm learning. So it's a balance given by lambda of how well to fit to a model and how well to fit to a data, where I'm trying to infer the entire system theta, essentially. But dealing with this balance can be quite difficult just via lambda. And still, the dimensionality of the inference grows with the amount of data that you receive, right? So you can imagine trying to throw this into some kind of SGD or machine learning style approach, and it could really struggle to infer this entire hidden state. And I found that from trying to do this with neural nets, for example, on this approach. So what if we take a step back And just look at, again, this little chunked problem, kind of a 4D var style thing. You might realize that these initial conditions U0 for each window could be inferred using data assimilation. So rather than just specifying a general optimization over theta and initial conditions, you might recognize that the initial conditions are a special thing to infer, that there are special algorithms designed to infer, right? And this is the job of data assimilation. And so many folks have worked on this. I'm probably folks in the room, including, you know, Marc Bouquet and Alberto Carrassi, and also Saïd Ouala and Ronan Fablé. So I'm going to tell you a little bit about those and then kind of a different flavor. But so just to give a short background, although actually, you know, sometimes I give this to the machine learning crew and you guys already know this stuff. But what's the point of filtering? You can define a filtering distribution as the distribution of my state U at time t, given a history of data, given knowledge of the model, and given some assumption about like the initial condition for the system, right? And so how do you often estimate these filtering distributions? Well, if I just switch to discrete time here, a lot of times we break it into sequential updates, right? So I can say that the next filtering distribution is basically a function of the previous. It's a function of my current measurement. It's a function of the dynamics that I know about that are governed in the model. And it's also a function of whatever kind of data assimilator I choose, right? It has some algorithm, it has some tunable parameters, et cetera. I'm abstracting all of that into theta dA here for the moment. And as a really simple example, I know I'm at the EnKF conference, but I'm going to try to convince you that if you can do it for 3D var, then it'll be even better with EnKF. Okay, so here's 3D var, which just says that my state estimate is a simple constant update of my prediction given by the prediction error of my system. And the parameters for this data assimilator are very simple. It's just the choice of this constant gain, right? And so in Kalman filtering, the whole point is to adaptively choose this gain based on covariances, but you could try to just use a constant one. And sometimes it works okay. Okay, so if I go back, I'm just going to introduce some notation to show you how, in the paradigm of machine learning that I've just shown you, how to insert the data assimilator into that paradigm. And so the notation is to say that, let me give myself this m hat, which is an estimate of the filtering distribution at the current time t, using a history of tau. Okay, so I look back a history tau, I run a data assimilator up to time t, and this is my estimate of the state at that time. Okay, so now all I'm going to do is put this m hat where the u0s were. Okay, and the point here is that now I've removed the dependence of my overall minimization that I probably want to throw into SGD or something like that. I've removed the dependence on the initial conditions, right? So now the initial conditions are implicitly defined by the dynamics and by a data assimilator, right? So all I have to do is minimize over the dynamical parameters and the choice of a data assimilator. And in that optimal, this initial condition will somehow be right? If I choose a long enough tau, then the assimilator will work. It will learn the initial condition, and then you will be well initialized, and will fit the data well. And so this perspective has, so what I'm going to show you is results from doing this joint estimation by coding the 3D var here in an auto-differentiable way, so that I can optimize this with gradient-based methods. And I want to point out some other like super relevant work. So there's Chen et al. So this is Becca Willett's group and Daniel Sanz Alonso. They also do something similar, but they do it with an auto-differentiable ensemble Kalman filter. So I think that's some very nice work. And they compare to Carrassi et al. In 2021, where they minimize a very similar function, but using alternating descent. So using an EnKF specifically to infer initial conditions and some kind of SGD to learn the dynamics. But instead of writing it down in this joint way where there's an implicit dependence, they do alternating descent, right? So you fix a theta you fix a model, use the model to infer initial condition, and then use that initial condition to infer a model. So sort of an expectation maximization idea. And so here I'm just going to show you like the approach, using this approach with 3D VAR and actually learning the gain matrix K for 3D VAR allowed me to learn a really good model for a very simple system that was surprisingly hard. So here's a simple case, Lorenz 63, where you partially observe the first, so you only observe the first component, you observe it with noise, you observe it, with a reasonable frequency, 0.01, and I gave myself 1,000 model time units, okay? And all I asked was, can I identify an ODE from only this information using no other knowledge that captures the dynamics of the first component of Lorenz 63. And there are all kinds of methods for doing this, also in discrete time, right? There's recurrent neural networks and there's reservoir computing. And you can try to do delays and lags and all these kinds of things. But I will tell you that from trying to just find an ODE in the space of neural nets, none of the existing approaches that I tried worked. And that is kind of what motivated me to try to do this, kind of auto-differentiable data assimilation style. So that's where this is coming from. So I think this is a really simple challenge. If you're interested in learning latent dynamics, can you find a model that does a good job of fitting the first component of Lorenz 63 using only that data? And so this is fine. The short-term prediction is good, but what was really the challenge was having good long-term statistics. So if you identify some model, most of the time I found that it would blow up after some integration time. Maybe I had to solve it for 1,000 time units or 10,000 time units, but it would leave the attractor. And so we were learning something that didn't have a stable, proper attractor. And I think it just came down to fidelity of inference. And so the method that I've shown you was just able to come up with a higher fidelity inference so that we could match the invariant measure, for example, of the first component of Lorenz 63. And so of course, this is just a toy example. I'm not saying that now we've done it, but recognizing that this problem is quite hard, even in really what we think of as very simple settings. If we don't know how these systems work and make no assumptions about them, it can be really difficult to learn from scratch. So hopefully this method may have some promise for discovering dynamics from data. And what's also interesting is that if we go back to this optimization, notice that I'm minimizing over both dynamics and parameters of the data assimilator. Perhaps you already know the dynamics, right? Perhaps you do have the equations for the system and you can integrate them. You can still use this approach by coding everything in, say, PyTorch to just infer parameters of the data assimilator. And so we were able to do that jointly with the inference, but you can do it alone. So the point is that we were able to learn gains for the 3D VAR that were better than our prior choices that we would have used for the system. So we found, this is just showing the solution it found, but I don't have the slides right now on this comparison, but I think it's interesting that this is another approach to basically trying to tune some DA methods. And you can think of it at a very high level. There's nothing that magical about it. You specify a parameter of the DA, and then you run it in a bunch of cases, and you evaluate how well it performed, right? And then you just do that a lot. And in this case, I'm doing it with gradient descent by coding all of the data assimilation in PyTorch. But you could also imagine doing it gradient freestyle with like a ensemble Kalman inversion or something like that. So here's another example. So bringing back to the Lorenz 96 multiscale example. So what's missing to me from the Wilkes paper is this epsilon equals 1/2 part on the right-hand side. And so I think there are many settings in science when we need to cope with problems like this, where there's non-Markovian things going on. And so if we were to just try to do residual modeling in that case, we would get, we got some infidelities, for example, in our estimate of the autocorrelation function. But applying the method that I just told you about, where it's trying to re-augment the state space, we got a much better match to the autocorrelation function. And so of course, in that toy example, we know what those hidden dynamics are, but the point is that exactly that we're going to pretend that we don't know and rediscover their influence, right? For motivated by settings when we don't understand how things work. And what's also interesting here is that for the Lorenz 96 setting, I really had to learn a good gain matrix for the 3D VAR. And what's interesting is that the gain matrix that it inferred, so I picked the gain matrix that it inferred corresponded really interestingly to the structure of the true system and the type of gain matrix you might build, right? In other words, it has a lot of the covariance structure of the fast dynamic or of the hidden dynamics. And so what you see in the vertical component are all of the states of the system. And in the horizontal component, horizontal axis is just the observed component. So what you see, first of all, is that the top part of K is basically the identity, meaning that there's a strong correlation between the first component and itself, right? And that second component and itself, et cetera. So there's a trusted kind of identity structure there. And then I took below that 9x9 square matrix on our observations. Below that, I reordered all of the rows of this gain matrix K using a hierarchical clustering to try to show me if there are subcomponents that are being learned that are consistent. And that's exactly what we see. So for example, this white brick here on the left, this is a collection of like 10 or 12 learned hidden components in my augmented system that primarily are learned to correlate with only the 0th component of the observation. And subsequently, there's a different brick of hidden components which are learned to mostly correlate to only the first observed component, right? And so if you look across, you'll see that it's kind of isolated. So while these hidden components are really connected to the 0th, they're not very connected to the others. And this is exactly the structure, or roughly the structure that we see in the original equations for Lorenz 96 multiscale. And so what's good news is that, inferring this type of object, or inferring covariances or something like that, can actually allow you to have a more interpretable machine learning model, right? Because before I just had some latent dynamics for this invented variable R, but now I can tell you a little bit about my belief on how those relate to observations. So maybe I'll stop here and pause for questions again. It's okay if you don't, but it's better if you do, I guess.
Can you hear me?
Yes.
So out of curiosity, I was thinking about whether your 3D bar estimate the K value, like what does it functionally mean in that system? Because if you're looking at it over the time and the K is basically interpretation of like difference, wouldn't it basically wouldn't it drive it to always, so in your system, does K change over time when you estimate it in this manner?
No, K is a constant. I mean, it's learned over iterations of an optimization algorithm. So that's all I was showing here, was just this is a optimization epochs. But it's the model for 3D VAR is saying that there's a constant gain matrix that is just used consistently. And the paper by Becca Willett's group and Daniel Sanz Alonso does this same sort of thing, but with EnKF, except they don't infer structure on EnKF. And this is why I chose to do this, is because I tried to run this same experiment with EnKF and the Lorenz 96 multiscale and have auto differentiation and infer the hidden dynamics. And I found it really struggled. And I realized the reason quite quickly is that if you were to run EnKF on the true system, it doesn't work very well unless you introduce localization or some other tricks. And so in the same way, you need to have some kind of localization in this constant gain. But this was learned completely from data. So I didn't tell it. So it's kind of interesting because it's basically discovering a localization.
I have a question. Because these augmented dynamics reminds me a bit of Kaufman operators of computer theory. Do you think there is a connection? You think it can be used for learning and augmented state dynamics for linear systems relying on linear operators?
So Koopman operator theory is certainly related in that, it is a way to learn a map for observables. However, I'm not sure how useful the Koopman operator theory is because it's really specified for an infinite dimensional object. And so what people do in practice is they look for some, combination of observables or some set of features that seem to approximate the Koopman operator in finite dimensions. But once you do that, it's not really the Koopman operator anymore. And so you can basically do everything that you do with Koopman operator theory without calling it that, and nothing really changes. So this is maybe just my complaint, is that I don't really know how to use the theory of Koopman stuff to do anything differently.
Okay, thank you.
I mean, that's probably just my problem.
Laurent Berthelot here. I'd like to bounce on the previous question and why the EnKF seems to struggle. So we have a very similar study in which instead of trying to learn the gain matrix, we learn the model error. And if you think of the orthogonal filter, the gain matrix is a large, large number of unknowns that only translates what you put in the model errors, which is much smaller dimension. So it's easier if you try to learn the model error than if you try to learn the Kalman gain. You reduce the number of unknowns drastically.
Mm-hmm. Yeah, so well, in this case, I'm trying to learn both. And so I found that I wasn't able to find, so the first thing I tried to do was use a basic forcing gain and just look for the model error. And I wasn't able to find it in this approach. Again, so when in the Markovian setting, it's not so hard, but the latent dynamic setting I found very difficult, especially for the for this particular multi-scale setup.
Marshall, I think I just want to remind that there are only 3 minutes left for you.
Oh, okay. Yeah, maybe I'll just finish up with a few slides. I mean, it's pretty much done. I'd rather talk with folks. I'm sorry I'm not there. So okay, I'll just give you the high level. So definitely agree with the last question that learning model error is the best thing you can do. Hybrid methods are great and can rescue incorrect models. Most of the time, it's better to start with what you know, and instead of trying to learn data from scratch or accept that you have a slightly imperfect model. Another thing that's relevant is choice of time step. So when comparing discrete time methods and continuous time methods, I'll just highlight that in this dashed orange here, which is a basic kind of data-driven discrete time method that I haven't talked about, that there's sort of a sweet spot of time steps. And if you pick too long of a time step to learn across, of course, that's a very complicated thing to learn because you're trying to predict very far into the future, but also it has inconsistency at short time steps. So just think about these kinds of things when you're thinking about trade-offs between discrete time and continuous time. I was going to kind of just preach more about exactly what the question was, which is that hybrid methods are the way to go. And the challenge is, learning them sometimes. But yeah, I think it's very interesting to fuse data assimilation and machine learning techniques for a variety of needs. And I think that you can use this kind of perspective to improve existing data assimilators. Might be able to cope with very long-term memory by using gradient-free optimizations. It definitely needs work. This isn't done. Maybe you can try to do something with parsimony by introducing sparsity regularizers. And then, yeah, I think that there's lots of applications for these kinds of approaches that everyone here is working on, from biology to systems pharmacology, climate modeling. I'm very curious what all of you are into. So let me just flash through some, important references. These are certainly highly relevant to the work I've discussed, and just want to thank the organizers and my advisor, the group at Caltech CMS. Do check out our paper, website, etc. Yeah, thanks. I think I'm on time. 9:59. All right. I see that Vikram has a question and he's on Zoom, so.
Yeah, we can.
Yeah, thanks. A quick one. Basically, can you hear my voice?
Yes.
Can you hear my voice? Yeah. So as someone who works in data assimilation, I like to see or hear root mean square error, RMSE. So in your example where you assume that the second component equation for Lorentz 63 is kind of missing and you apply your technique, did you do an experiment with assuming that you know all the three equations, do an EnKF experiment with the same observations, come up with the RMSE, and then find out the RMSE from your method and compare the two? So what you get is a baseline where you know that the second equation exists and what it is, and then you can make a statement about your technique, how close the RMSE gets to the baseline.
I didn't for this. And the reason is that I wasn't really that motivated by short-term prediction. I showed you some plot and it fit some stuff. I'm not claiming that it's that good. What is really hard to get is learning a system that has okay, even like reasonable short-term prediction that has long-term stability. So I actually didn't do the in-depth experiments there because to me, this is the surprising plot, is that I was able to learn a model that was okay short-term forecasting, but reproduce the invariant measure. So I was much more interested in this case. And we did a much more careful analysis of the kinds of things you're discussing in the fully observed case when I was learning Markovian model errors. So that's what like these plots are showing, validity times, comparing things and stuff like that.
Okay, all I'm saying is that for a data assimilation person, if someone claims that I have a new technique, whatever, the first question I would ask is RMSE. So.
Yeah, thanks. Yeah, I mean, I think I still view this as more research. And so my concern is that if somebody gives me a model with good RMSE, but if I run it for too long and it blows up, that really upsets me. And so that's actually the motivation for this work, is trying to make sure that even if it has good short-term RMSE, that the model doesn't blow up in long-term, because I think that this can improve kind of trust in models. So just trying to just learn what kinds of methods will promote long-term statistical reasonability.
Thanks.
Yeah. Yeah, so I'm not trying to deploy this. I mean, I believe you that there's a lot in between what I've told you and operations.
Thanks.
Thank you.
Okay, the time doesn't allow us for any more questions. Let's thank Matthew again for a very nice talk.
Thank you.
We have our last speaker of the day is Yishuan from Caltech. He will present the sampling method based on second order Langevin dynamics. So let's see. Here's the speaker.
Here's, yeah. Oh, yeah.
I need to share your.
Yeah.
Oh, it's
Full
already.
screen. It's not full screen. But it's not full screen.
It's not a full screen. Yes.
Maybe we should view. Yeah.
Yeah.
Can you show me how to use this?
I think you can use just your speaker.
Oh, thanks.
It's okay. You are the last talk, so.
Oh yeah, sure. Thanks, Andres and Xiaodong for the introduction. Oh, okay. Like this. It looks down.
It's okay.
But it's on speaker. Okay. Oh, cool. Yeah, it's been a long day, and actually, my topic is a bit off what you're like used to. It's like sampling mathematics, so I don't wanna bother you. Like, I hope you enjoy my talk, and because my topic is a bit distant, so I would like to encourage you guys to interrupt me at any time and ask questions, so that you won't get lost in the middle or even in the beginning. Well, I'm gonna start. So the topic of this talk is a sampling method, and we call it ensemble Hamiltonian Monte Carlo. So it's an ensemble method based on the second order Lagrange equation. This is a joint work with my friend Ziming and also Andrew Stewart from Caltech. So firstly, it's a sampling method, but I would like to cast it in the context of a Bayesian inverse problem because, you know, like solving Bayesian inverse problem can be cast into a sampling problem. And in this perspective, in the Bayesian inverse problem perspective, connections can be made between this sampling method and the ensemble common methods. So I believe you are pretty familiar with the topics. So like our setting is a Bayesian inverse problem. So we have a known but possibly a complicated nonlinear forward mapping, a G, and we have like a Gaussian noise in our observation. Our objective is to infer the posterior distribution of U based on this forward model. Special task we want to achieve is that we want to solve the inverse problem without resorting to the derivative of a G, because as I emphasized, in practice, a G can be like a nonlinear and pretty complex, and sometimes a G is like a differential operator, so it's hard to compute its derivative. And in our examples that where it's deployed, so how do we do this in context of a Bayesian inference? Well, we have a prior on the a noise, and we have a prior, assuming it's Gaussian, we have a Gaussian prior on the parameter U, and based on the Bayesian law, we know that the posterior of U, pi U here, is proportional to the loss or to the arrow from the model and observation y. So that's the first term, and also the Gaussian prior. So at the end of the day, we would like to sample the distribution pi U that is proportional to the exponential of the function phi r U, and phi r consists of a loss term and a regularization term. So because it's a sampling problem, in this section, I'm going to introduce first along the dynamics that what we normally use for sampling problems, and then we're going to introduce our proposed Hamiltonian Monte Carlo method. Okay, so to start with, in this equation 4, we have the like a normal Lagrange dynamics. So for particles are evolving according to the Lagrange dynamics, they would converge to the desired posterior distribution which, if you recall, is the exponential of a minus phi r u here. So the drift term is determined by the potential, which is the invariant distribution. So in practice, if we adjust around the Lagrange one dynamics for the posterior, in practice, it's going to be slow, and the convergence speed is highly dependent on the potential phi r. So Andrew and his collaborators in 2020, they proposed a ensemble preconditioner of the Lagrange one dynamics. So what they do instead is, on top of 4, they multiply it by a preconditioner, and this preconditioner is given exactly by the ensemble covariance. So like I see you here. In theory, for any given preconditioners C, the Lagrange one dynamics in the form of a 5. Try to what? Keyboard. Oh, okay. Never mind. Huh?
Maybe the computer is not responding like this one. Yeah.
It is, no, I just want to
okay.
emphasize the it's not working, so it's okay. Yeah, for in general, for any positive definite matrix C, we can use it as a preconditioner to increase the convergence speed of the Lagrange one dynamics. But Andrew and the collaborator, they found that if in particular we precondition it with ensemble covariance or ensemble covariance, we can achieve like fast convergence. And also a merit of that is that for finite particles, we can actually discretize this Lagrange one dynamics in a form that we don't have to resort to the derivative. So this term, like the gradient of psi r, as you can imagine, they would be dependent on the gradient of G, which, as I emphasized, might be hard to compute. So the preconditioner they proposed can boost convergence and result in a derivative-free algorithm. But in reality, we know that sometimes the first order Lagrange one dynamics, even with a preconditioner, they can be slow. And intuition from the physics community is that if we introduce an auxiliary variable, and if instead of first order Lagrange one dynamics, we resort to the second order Lagrange one dynamics, then with the help of the auxiliary variable, we can accelerate a mixing and achieve like a faster convergence speed, which is actually rigorously proven like recently. So just for those of you who are not familiar with a second order Lagrange one dynamics, so on top of the potential phi r in the state variable, here we call it a q here, we introduce a velocity or a momentum variable p. So now the Hamiltonian is a quadratic form in p plus the potential form in q. And we consider the joint evolution of the variable p and q. So here in equation 7, we consider the second order Lagrange one dynamics in now a state, another particle, another domain of particles in R2n, because we augment the state space with the velocity space. And of course, I think first order long-term dynamics, we can do a preconditioning in the hope to achieve a better convergence. So here we can like equation 7 is it's a general form of preconditioning. So we can precondition the potential form with a diagonal and a skew symmetric part. And after preconditioning, the equation 7 still has the desired posterior distribution. So when it converges, the particles, when we consider the margin distribution in a Q, they still have the desired posterior distribution. So remember the goal we want to achieve is first we want to achieve fast convergence. Secondly, we want to obtain a derivative-free algorithm. So to be specific, here is how we choose the preconditioner. This can be like it's essentially the preconditioner is also dependent on the ensemble or covariance. So we arrive at equation 10. And once we dive into the finite particle scenario, you'll know why this choice makes sense, because we can we can use some ensemble approximation to get rid of the derivative. Just to see this a second order Langevin equation with conditioning, it has a associated nonlinear Fokker-Planck equation, and in particular, the preconditioner is only dependent on the density distribution, which is a covariance, but not dependent on the particle position at Z. So this nonlinear Fokker-Planck equation, of course, has a posterior distribution as its invariant distribution. Okay, in this part, from the continuous in time sampling algorithm, I'm going to introduce its a time discretization and also a finite particle approximation, so that to use it into actual problems. And in this part, we will see why this algorithm makes sense and why it's derivative free. So it's actually pretty easy. So we approximate the covariance by the ensemble approximation. So that's equation 12 here. And because the specific sampling problem we consider, it's in the context of inverse problem. So the lost on observation, if you remember, it's a y minus a gu to some some quadratic form. So if we plug in all of this into the algorithm, and after some calculation, and if we approximate the gradient by a finite difference. Then like from from equation 14 and 15, that's what we obtain for our ensemble based algorithm. As you can see, the algorithm now it's a derivative free, so it's numerically trackable. Moreover, we have some additional theoretical properties of this algorithm. Firstly, we can introduce a correction term because remember in this finite particle algorithm, we approximate the covariance by its empirical approximation. So if we just run that algorithm, then it no longer preserves the invariant distribution, but we can easily introduce some corrections that are also trackable to find a finite particle approximation of this interacting equations. Secondly, this algorithm is a phi invariant, which means that we have a same convergence rate upon affine transformations. So as an example, if the desired posterior distribution is a Gaussian, then the convergence speed is uniform because like it's the same upon affine transformations. So I imagine traditionally for the Langevin equation, if the posterior distribution is Gaussian but skewed in a certain directions, then it's very hard for particles to like go to those directions, and a mixing time is going to be pretty long. But our algorithm is a phi invariant, which means that we can achieve a good convergence rate. And that's also why we want to use a preconditioning. Finally, we have some theoretical properties of convergence in the linear case. Also, we can mathematically prove that in the linear case, if we start with an Gaussian initialization, then using our algorithm, the distribution of particles remains Gaussian. And of course, by affine invariance, the convergence speed is uniform of the operator. I just remark for nonlinear cases, I think it's very hard to prove theoretical convergence of nonlinear things in general for sampling methods. We're still like it's probably a future work. And finally, I'd like to present some numerical results. The numerical results are basically a comparison of this ensemble precondition, like a second order algorithm as compared with the first order version, just to see like why this second order algorithm makes sense. So the first example is English problem. It's an elliptic boundary value problem. So the boundary condition, one of the boundary condition U2 and also the elliptic operator parameterized by U1, they're unknown, and we have some measurements on the interval, and we're trying to infer a U1 and a U2 based on observations. The plots, as you can see, are comparison of our second order algorithm EHMC with the first order algorithm EKS, you can see that in all of the quantities we cared about, the second order algorithm converges faster and it's more stable. And on the leftmost plot, you can see that it's similar or a representative of the true underlying solution. And the second example, it's a more evolved, like a 2D Darcy flow problem. So it's we know the right hand side and the solution or the measurements of solutions of this a Dirichlet boundary elliptic problem, and we are asked to infer the operator or infer the property of the medium, the function AX. And here we model AX as a Gaussian field. And we also compare the second order algorithm EHMC with the first order algorithm EKS. It's on different plots. So on the top, it's the results obtained by EHMC with a different number of particles, and on the bottom is the results obtained by the first order algorithm with the same number of particles. You can see like quantitatively it converges faster, like it decreases faster to equilibrium. Yes, that's pretty much I want to talk about today. Are there any questions?
Do we have any questions?
Oh, what time is it? Oh.
Thank you. Wonderful talk. So I was wondering, so for both of the Langevin dynamics and for the Hamiltonian that you're doing, you also have this gamma naught that this comes from the prior. So how do you know what the gamma naught is?
Oh, yeah, thanks for the question. I think in our settings, we basically assume we know the gamma naught. So here we are like we assume that the prior is a given, but in practice, of course, it's a good idea to play with different priors. To see, I think that's a general problem of Bayesian inverse problems. So you always need to play with a prior, but in terms of our algorithm, it's at the end of the day it's a sampling algorithm. So you always assume your desired posterior distribution is unknown, but in the context of inverse problems, how to choose the prior and therefore the associated posterior. It's
But I mean, also in the numerical experiment.
Oh,
you show, yeah. So like in the numerical experiment, you showed what was the gamma? I mean,
oh yeah. So like here, we just choose some normally how people parameterize gamma for the Darcy flow problem. So they choose a log Gaussian field with some regularizations, and this is some hyper parameters that you need to tune.
Great. So thanks for a very nice talk. So I guess the question probably is already answered on the last slide, but maybe you said that and I overheard it. Basically, is your method just a sort of just a generalization or generalization of the ensemble common sampler to the techniques?
Yeah. Yes. Thanks for the question.
And what about the computational cost when you compare these two?
Oh, it's a comparable because I didn't put in here the actual numerical algorithm involving the discretization, but of course you double the state space and stuff, but it's comparable. Yeah.
Maybe.
So I have a question about the time integration of the ODEs you showed.
Yeah.
Because of the nonlinearity of the problem, does it require some precaution?
Require some what?
Precaution, like to be careful.
Oh yeah. So we just use like normally how people are do. So we split this C equation 14. We split it into the Hamiltonian part and all you process part. And for the Hamiltonian part, of course, we should use some asymptotic integrator, but it's just a standard one. There's nothing fancy.
Okay, thank you very much.
Thank you.
Yes, again, a question. So also in the same direction as I had before. So I mean, in the classical sort of Langevin sampling, they, as you said, right, because the overdensity is pretty slow, they were more heuristic, right? They do the second order, and then what they often do is also something serious, right? They keep the drift constant for a time, and then after some time, so let just or sorry, it's the other way around. So you let the drift go, and then after some time you give some noise to the system. So have you also looked at trying to generalize the ensemble common sampler into those more?
Just to make sure I understand your question, are you suggesting that to change the amplitude of the noise?
So no, it's more like I mean they have, so from these Langevin dynamics, I think you can put it more general. So they do some pretty advanced stuff in order to increase the speed of convergence to these. So they went further from second order dynamics, I think. And have you looked, or is there a future plan to also sort of develop the ensemble common sampler into that direction? So,
I'm still maybe we can discuss offline, but I just want to mention that in what we do and what the ensemble common sampler there's a adaptive way of increasing or decreasing the noise. So like on the CPU and square CPU here, there's a extra factor gamma. So like a gamma times CQ and square root 2 gamma times CQ. So a gamma can be chosen adaptively, and also the time discretization can be chosen adaptively. I'm not sure if that's what you're referring to, but
it goes into that direction. So yeah.
Oh, sure. We did that.
Yeah, thanks.
Thanks.
Okay, time is up. Thank you again for a very nice talk. Let's thank all the speakers of the day and everybody who stayed the entire day. Thank you very much.
The dinner will be at 7 o'clock. It's not 6:30.